Okay, hello everyone. Welcome back to the stream. It's been a couple weeks. How are you all doing? Let me know if you can hear me. Last time we had a bit of a problem with my audio at the start, so I just want to make sure that everything's good before I start talking. So just let me know in the chat if you can hear me. Check. Okay, sounds good. Great. All right, so welcome back to the stream. Last time we had a great stream with Donald, aka the packet thrower. He showed us some CCNA wireless topics that you have to know for the CCNA. And today we have another repeat guest, that is Kelvin Tran. So I think this is his third time on the stream. First he showed us some Juniper, then last time he showed us MPLS, and today he's going to show us another very important topic, that is multicast. So multicast is something that I briefly mentioned in the CCNA course, but you don't really have to know it in depth, or you really don't have to know it in depth for the CCNA. So I mentioned basically like unicast is one-to-one to one destination, right? Broadcast is one to all possible destinations in the subnet. And multicast is one to many or one to multiple. And you should know things like the OSPF multicast address 224.0.0.5 or .6 for DRs, BDRs. So that's basically all you have to know for the multicast for the CCNA. Now for the CCNP and especially the CCIE level, you do have to know multicast in depth. It's a very important topic. And Kelvin, I believe, is actually studying for his CCIE right now. So yeah, let's see how that's going. I'll bring Kelvin on. And you're on. Hey, Kelvin.
Hello.
Hey, welcome back. How's everything been these days?
A little crazy.
A little crazy.
I'll admit. A little crazy. Doesn't help that Omicron's been
Yeah,
released
right,
into the
right.
wild.
Yeah, exactly. How's the CCIE studying going?
It's going well. It's just under, I think, I can't do math, just under 40 days-ish left until the lab exam, assuming that I don't have to reschedule because of Omicron. So low uncertain right now.
Yeah,
They
that's
did
true.
end up shutting down Cisco Live Amsterdam, so I'm just a little bit concerned.
Right, right. Yeah. Well, hopefully you can do it according to schedule and finally get that number.
Yeah, let's go.
Yeah, let's go. Hopefully I'll be in that position in a few years. We'll see. Yeah, we'll see about that. So what are you going to show us today?
So today is going to be multicast day. So we were bantering a little bit before stream. It's 2 for 2. MPLS and multicast are both topics that people either love or hate. So we'll see how it goes here.
Yeah. Let's see what you guys think of multicast today.
Yeah, multicast it's a bit of a weird subject there. There's a lot of practical application for it, especially in things like unified communications, so collaboration, VoIP, that fun stuff. Paging uses multicast extensively, so there's applications for it, but it's also a little bit of a pain to study because it deviates significantly from some of the paradigms that we've established in unicast routing. So it'll be an interesting journey when you guys start getting into multicast if you haven't already.
Yeah. So
and if you haven't already, then this stream's for you.
Yeah, here's your chance. So who should study multicast? When should you start getting into it?
So honestly, as far as prereqs go, there's not much you need to know besides having a good CCNA grasp on unicast routing. And if you want to study IPv6 PIM, which I'm not sure if we'll have time to cover here, if we do, I'll cover it near the end. But if you want to get into things like PIMv6 and MLD, which is the IPv6 implementation for multicast, you do have to have a good grasp on IPv6. But besides that, there's not much you need to know in order to get into multicast. Just having your CCNA is probably enough for you to be able to figure out the nuts and bolts of it. As far as when you should study multicast, really depends on you. If you're going for a cert that requires that you know multicast, then that's
right.
very self-explanatory. If your work deals with multicast, because a lot of places do, particularly again with things like collaboration applications, then definitely multicast is a useful skill to have in your arsenal.
Yeah, right. Okay, sounds good.
Yeah.
So you mentioned certs. Which certifications require multicast? So, for example, at the CCNP level, CCNP Encore or the Enterprise,
Yeah.
what do they need to know?
So for the Encore exam, I literally just looked at it before the stream started because I forgot actually what Encore expected of candidates as far as multicast went. They just want you to be able to understand the function of multicast protocols. So understanding the role that protocol independent multicast plays, understanding the role that the Internet Group Management Protocol plays, or IGMP. If you have a good understanding of PIM and IGMP and the overall integration of multicast into an overall network, that's probably good enough for Encore there. They don't get too deep into it, which is reasonable. I quite frankly had expected in NRC, but it's not there. And Encore is really more of a shallow, broader exam there, so it makes sense that they wouldn't cover it too much in Encore, but it's a little surprised it's not in RC. As far as the other tracks go, a lot of the other tracks rely on multicast. So I mentioned collaboration. There's a lot of multicast there.
Yep.
Data center has multicast. Service provider has multicast. And that's about the extent of that. And for the CCIE tracks, that's true even more so.
Yeah, for sure. Yeah, that's where you have to really know it and be able to configure it, implement it, right? At the CCIE level.
Yeah. And even at the CCNP level, the service provider and the data center tracks, there are no jokes because, like, for example, for the data center track, you see multicast come in for when you start configuring things like VXLAN. So flood and prune in VXLAN utilizes a multicast tree. So for things like VXLAN and the data center track, that's where they'll start throwing in some PIM. Service provider is going to cover the service provider side of running multicast. So there's quite a bit there.
Okay, cool. So are you good to go? Shall we?
Yep.
Can I get you to screen share and let's get into it?
Yep. So I'm going to go ahead and throw up my CML here, which I forgot to do before the stream started.
And as you guys are watching, feel free to ask any questions in the chat. I'll throw them Kelvin's way.
Yep. Okay. So if I remember how to screen share here, let's go ahead and go for this screen. All right, we're good?
Yep, let me put you full screen. There we go. All right, good to go.
Hey. So this is going to be, as is the case with my other streams, and for the most part, Donald's other streams too, this is going to be very lab intensive. So we're going to really be showing you how multicast can be implemented in a lab topology here. So this is the topology I'm working with. And we've got 15 routers here. I've honestly lost count. We've got 15 routers and we've got 7 hosts. Now, the reason that this topology is so wide, for lack of better words, is because there are a lot of features that I'm going to be showing here, that I'm going to be trying to show anyway, as time permits. And having a lot of routers in this particular topology makes demonstrating each feature easier. But if you're just labbing multicast, honestly, you don't need this big of a topology. Just a couple routers here will be enough for you to lab a lot of PIM, IGMP, things like that. So that's the reason for this topology spanning so wide. It's not because I'm actually going to be working on all 15 at the same time. That would be kind of insane. So for the first time, I'm going to move these out of the way here. I think for the first time ever on a stream, I've actually configured all the IP addressing before the stream.
Nice.
So
awesome.
Yep. I know, right? Preparedness. So what I've got running here, it's a fairly stock configuration. I've got the point-to-point Ethernet circuit set up between all of the routers and all of the hosts. And then I've got loopback interfaces on all of these routers here. And then I can show this because all of these routers are running the exact same configuration for the most part. EIGRP is running within all the 10 networks and all the 192.168 networks. So what we have here essentially is a working unicast topology. So if I'm on R1, I can ping 13, let's say, and it works. And the reason this is significant, and the reason I pre-configured all of this, is because multicast, the expectation is that you have a working underlying unicast topology, because PIM doesn't actually exchange any topology information. You learn unicast routing protocols like OSPF, VIGRP. Those guys exchange information about the topology. OSPF has a link state database, and that builds the SPF tree, which is the representation of the topology from OSPF's point of view. Here, PIM doesn't actually exchange any topology information. It's purely responsible for exchanging multicast state information. And we'll get into the types of multicast state, but it's not like your traditional routing protocols. It's relying on the fact that there is an underlying unicast topology that it can use to build the multicast trees.
Okay. So multicast doesn't replace unicast. It has to work on top of a working unicast network, right?
Yep, it works in tandem with unicast.
Okay, cool.
So what we can get started with here is there's two main protocols that we're going to focus on today. PIM, which is Protocol Independent Multicast, and Igmp, and which is the Internet Group Management Protocol. And these two protocols have very distinct places. So the purpose of Igmp, for the most part, is going to be, in our case, to signal interest. So you mentioned at the beginning that multicast is one-to-many, and broadcast is one-to-all. So in IPv4, you don't subscribe to a broadcast. The broadcast gets sent out, and you process it. So even if that message isn't necessarily intended for you, like let's say it's an ARP request that's not intended for your IP address, you still have to process it. You get down to the payload before you realize, hey, this isn't for me, and you drop it. That's a wasted process. You have to go past the Ethernet header, go past the IP header. You have to get down to the payload in order to realize that this wasn't for you. With multicast, you're subscribing to a particular group. So you're sending your traffic, you're sending your stream to a particular multicast group. And then all of the devices that are interested in receiving traffic from that multicast group will receive traffic from that multicast group. Now, there's two main approaches to determining interest. There's the dense mode approach, and then there's the sparse mode approach. The dense mode approach is basically, and the main difference between these two is the starting assumption. So the dense mode starting assumption is that everyone in the topology is interested. So you can see here, I've got these 7 hosts here: host 1, host 2, host 3, host 4, host 5, host 6, host 7, get the point. If I were to run PIM dense mode, which I'm not going to, if I were to run PIM dense mode throughout this entire topology, the assumption is that everyone is interested. So if I had, let's say, host 1 send some traffic to the multicast group, the network would essentially replicate this across the entire network, such that host 3, host 4, host 5, 6, and 7 all get traffic. Now you might think, well, how is this different than a broadcast besides the fact that it's routed? Well, with dense mode, the idea is that the receivers that are not interested need to specifically, and I should be more specific, the routers that are connected to the receivers need to specifically say, hey, I don't have any interested receivers on this end, so I'm going to go ahead and prune myself out of the multicast path. And that's how dense mode eventually achieves having only interested receivers receive the traffic. It starts off assuming that everyone is interested and then relies on the routers on the receiving end to say, hey, I don't have any interested receivers. And the way that those routers learn about those interested receivers is through Igmp. The sparse mode approach takes the direct opposite assumption. It starts with the assumption that no one's interested. And then as receivers subscribe to the particular multicast group using the Igmp protocol, the routers that are connected to those receivers register their interest, communicate that using PIM, and then at the end of the day, you're not wasting all this multicast traffic. You're not replicating it to hosts that are not interested, because your assumption is that everyone's uninterested at first, and then you're adding on interested hosts as they come in.
Okay, so am I correct to assume that sparse mode is preferred?
Yes.
Okay.
It's preferred so much that the CCI doesn't even mention dense mode,
Okay, there you go.
with some exceptions. So as we'll see later, we'll actually see dense mode once here. We're not going to be specifically running dense mode across the network, but we will see dense mode once, because there are some scenarios where sparse mode fails to be able to signal the multicast, and we'll see that with features like auto RP, which I'll again cover later. So there are uses for it, but for the most part, you don't want to be running dense mode across your entire network.
Okay, got it.
Okay. So as I mentioned, Igmp there is used for the receiver, so in this case, the hosts, to be able to signal to their directly connected routers. So in this case, it would be probably their default gateways. For them to be able to signal to the multicast routers that I'm interested in this group, and I want to be able to receive the traffic from a source that's sending traffic to that group. So that's the purpose of Igmp. And then PIM is used to actually handle the multicast routing. So PIM is used to exchange the multicast state information across routers. So what I'll do is I'll enable PIM across the topology first. That way we can see PIM neighborships coming up. And then what I will do is go ahead and cover how Igmp works. And we'll cover the different versions of Igmp. And then we'll move on from there. So again, we have this unicast routing topology set up. So I've got EIGRP running. So from there, enabling PIM is really super easy. You just go under the interfaces. So in this case, what I'm going to do is I'm going to activate PIM under all of the interfaces that are IGP enabled. So that would be gig 1, gig 2, and loopback 0. And that's going to take enabling on all of these routers here. So it's just the IPPIM sparse mode command under the interface in order to enable PIM. There's also IPPIM dense mode if you are so inclined.
Okay, so if you enable PIM on the interfaces, they'll start like sending hellos to their neighbors or to find neighbors?
Sending PIM. Yeah, so it's similar to something like OSPF. You enable OSPF on interface, it blasts out hellos.
Got it.
Same thing here. There's also PIM dense mode, and if you're so inclined to enable dense mode. And there's also one additional command, IPPIM sparse dense mode. Now, List is a hybrid of both, as you might be able to assume from the command. So if you're running sparse dense mode, what the PIM router does is it will run sparse mode on that interface. But if for whatever reason, like I mentioned earlier, there are scenarios where sparse mode fails, if for some reason there is a particular group that cannot be signaled via sparse mode, let's say because there isn't a rendezvous point for it, which I'll cover later, then it will fall back to dense mode. So if sparse mode fails, fall back to dense mode. That's what sparse dense mode does. But it still primarily will try to use sparse mode and prefer it to dense mode. So that's that command. But we're just going to be enabling IPPIM sparse because I have no reason to be enabling IB sparse dense yet. And as I enable these, you might be able to see, if I don't switch away fast enough, that we have PIM neighborships coming up.
Yep.
So
there you go.
Here you can see we have PIM neighborships coming up. And again, this works much like OSPF. You just enable on the interface. It's not nearly as complicated as MPLS, where you have to consider router IDs and reachability of those router IDs. It's really just enable PIM, and they will form neighborships with each other, much like OSPF or EIGRP would. And the general principle here is that you can never enable PIM on too many interfaces. That's why I'm looping the loopbacks in here. So if you're wondering, if you're scared, like, oh, I might enable PIM on too many interfaces, My general recommendation there is that you can really never enable the too many interfaces.
Is there a need to configure passive interfaces, for example, on loopbacks, like you do in OSPF?
You can. Well, not necessarily on loopbacks. You can. There is an Ippmrp passive command.
Okay.
It's slightly different. I'm probably not going to cover the Ippmrp passive command. I'll probably just run Sparse on all interfaces. But if you're interested, you can Google the pim passive command. And as I recall, Cisco has pretty good documentation on it. But generally, if you're trying to do something like with OSPF passive interfaces, where you're trying to prevent neighborships from being formed, or you're trying to prevent the OSPF domain from going too large, you can run things like I'm not sure if I'm going to have time to cover it, but there is a feature called Multicast Boundary. And in fact, Donald was mentioning it in the Discord before we got here. There is a feature called Multicast Boundary that will let you, as the name might suggest, set a boundary for how far you want your multicast domain to go. And so that command would be Ippmrp multicast. I'll find it later. I forget the exact command to enable it.
I noticed in some of the messages on that router, it said DR change. Does PIM have like designated routers like OSPF?
It does, yeah.
Okay, interesting.
And we'll get into that later. Yep, DR change. Yep.
Cool.
So that's the last route I have to enable PIM Sparse on. So we've got PIM Sparse enabled on all interfaces at this point. Now, we need to talk about, before we talk about RPs, we need to talk about multicast route types. So that's going to make understanding this a lot easier. So with PIM sparse mode, you've got two types of multicast. Let me see if I can pull up my Corel painter here. We've got two types of multicast route types. We've got what are called S, Gs, and we've got star, Gs. Fairly intuitive name. Now, S here stands for source, and then G stands for group. And then this asterisk represents a wildcard. So your S, G route type is going to specify a particular source sending to a particular group. So an example of a S, G route type would be something like 192.168.3.3, and then let's say the group is 239.1.1.1. So this is the source that we're sending the traffic from, and then this is the multicast group that the traffic is directed towards. Now, star, G route would, for this same group, would look something like this. And the differentiation helps solve one of the issues with, in this paradigm, is called any source multicast. So what we're talking about here is multicast where we don't care what the source is. There is source-specific multicast, which I will definitely cover later. But what we're covering now is any source multicast, PIM ASM, which means that we don't care what the source is. If there is a source that is sending to this particular multicast group, I want my receivers to receive that traffic, regardless of what that source IP address is. So with any source multicast, you have the issue where if you're a source, I almost dropped my pen there. If you're a source and you're sending traffic to a group, that source knows about the group, but it doesn't know about any receivers. And if you're a receiver, you've got the exact opposite issue. You can join the group. You can say, hey, I want to receive traffic from all sources that send to 239.1.1.1. That's the multicast group. But you don't know what the source is. So it's a chicken and egg problem there. The sources don't know the receivers, and the receivers don't know sources. So that's where the concept of a PIM rendezvous point comes in. PIM rendezvous point is one router that is the root of this tree. So if you think about a tree has a root in the ground, and everything blossoms out from that root. So when we talk about multicast trees, a tree structure being, you think about like spanning tree, that visual in your mind is kind of what we're talking about here. Because you can have one source and that one stream of traffic splits out into multiple receivers, we conceptualize the multicast signaling in terms of trees. Now, trees have roots. So the root of the tree that is defined by the star comma G here is going to be the PIM rendezvous point. And then the root of the S comma G here is going to be the source. Now, the point of the rendezvous point is to bridge the sources and the receivers. So again, sources don't know the receivers don't know the sources. But the RP is a router that is configured on every single multicast router in the topology. And the point is that the RP is going to receive all of these messages from interested receivers. So the receivers are going to use Igmp to tell their directly connected routers that they're interested in, let's say, 239.1.1.1. From there, that multicast router that's directly connected to your receiver is going to convert that into a message called a PIM join, which I'll do a pack capture on later. A PIM join that gets sent up to the RP. So at this point, the RP knows that there is a interested receiver there for the group, so it registers it. And if more interested receivers come on, that process repeats. So the RP gathers all this information about receivers that would be interested in traffic going to 239.1.1.1, regardless of the source. And then let's say that there is a source that comes online, let's say 3.3, sends traffic. We are going to send what's called a PIM register. So the directly connected router to the source, once it detects that there's multicast traffic that's being sent towards the topology, towards the network, it's going to send a PIM register message. So the PIM register message is going to create our S comma Gs, and then the PIM join is going to populate our star comma Gs for the most part. So we'll see that PIM joins can also be used to populate the S comma G later, but this is a simplification that we'll roll with for now. So the joins indicate the receivers, and then the registers indicate the sources. That's a better view there. So when the RP gets this register message that, hey, there's a source that's sending traffic to this multicast group, what it's going to do is it's going to allow traffic to flow between the star comma G and the S comma G. So remember, the RP knows where the receivers are. And now it knows because the PIM register message was sent from the router directly connected to the source. Now it knows where the sources are. So there's one router in the topology that knows where both the sources and the interested receivers for that multicast group are. And so it's going to take the traffic that the source is sending and it's going to route it down to the receivers. So now we've got a working multicast flow. So the source sends its traffic to down to the RP, and then the RP is going to bridge that with the interested receivers. It's going to send that multicast traffic down towards the receivers. So that's a brief, hopefully, rundown of the difference between S comma G and star comma G state types, and we'll see both of them when we implement multicast routing here.
Okay, sounds good.
I know it's a lot of information, so are there any questions in the chat that I need to concern myself with?
Nothing about that. Seems good. I think that was pretty clear.
Okay.
Yeah, sounds good.
Cool. And again, if it seems confusing, a lot of it is a lot. And when you see multicast in action, just like with MPLS, just like with a ton of other technologies, when you see this in action and when you see how this actually works, hopefully it's going to become a lot more clear for you. So we have PIM up. So show IP PIM neighbor. So we have PIM neighborships here. And this is PIM v2. Now, what I am going to do here, before I forget to, because this is a really common mistake, believe it or not. So we assume that IP routing is enabled by default, right? When we go and do IP routing with Unicast, so OSPF, for example, we assume that we have IP routing enabled because it is a default configuration. But you can also turn off IP routing. So with multicast routing, that's not the case. With multicast routing, it is not enabled by default. So right now, if I do a show IPM route, what we should see is a message at the top that says IP multicast forwarding is not enabled. So you can form your PIM neighborships all you want. You're not populating a multicast routing table. And this is the command to view the multicast routing table, by the way, show IPM route. So even if you have PIM enabled, you can signal the PIM you want. You're not populating your multicast routing table until you have IP multicast routing enabled. So we can go ahead and enable that. So I'm going to send this to all connected routers because all of these routers need to have multicast enabled. And the command to do it depends on the platform. So there are some older platforms. I'm thinking of more like iOS 15. So these are iOS XE routers, just for reference. These are CSRs, I believe. I think I use CSRs. Yeah, I use CSRs. So these are iOS XE 1703 routers. Now, the significance of that is that the multicast IP multicast routing command is going to have to be followed by distributed. And this is just to do with the architecture. In iOS 15 based platforms, if you just run IP multicast routing, it'll work. If you're running iOS XE, you have to add this extra distributed flag because of the forwarding architecture for these XE platforms here. So we'll go ahead and run that command on everybody. And now if we run show IPM route, there's a couple of things here. A, we've got a star comma G here. This is a background process here. And B, you can see that message that we had above about IP multicast forwarding not being enabled, if I can get it here, is now gone. So we have IP multicast routing working. So the next thing we're going to go ahead and do is configure a RP. Now, you have to think about this very carefully, and there's an art to designing where your RP is going to be. So you might recall in my explanation what an RP is, the RP's role is to bridge the sources and the receivers together. So the sources send their traffic up to the RP sends the traffic down to your receivers at first. Now, what that means is that the RP is going to be in the data path at first. We'll get into that at first stipulation later. So the RP is going to be in the data path, which means that we don't want the RP to be somewhere, out in the out to outer space in the moon somewhere, right? Because that means that we'd have to traverse all of these hypothetically existent routers to get to the RP, and then traverse them back down to get to our receivers. That's really inefficient, and that's a really dumb way to design a network. So we need to have very careful consideration about where we put our RP, such that it is a centralized, to some extent, a centralized device in our network. So here, for example, we can make our RP R4, but it wouldn't necessarily make sense to make our RP R13 or make our RP R15, because that means that even if I want to send to a multicast receiver over here, I'd have to come down here to my RP and then come back over here to my receiver. That, again, doesn't make sense. So we want to, again, make sure that our RP is somewhere that makes sense. So here, I'm going to go ahead and pick R4, just because it's relatively central in our topology here. So there's not a big disproportionate impact for any of our multicast receivers if we were to pick R4. So R4 is going to be our RP. So now we've made that decision. There's a couple of other things that we have to consider. There's a bunch of ways to assign a rendezvous point. Now, just to get this working, what I'm going to do is I'm going to statically configure the RP. Remember, all of these routers that are doing multicast forwarding have to be aware of the rendezvous point. So the command to do that is going to be ippm RP address, and then we're going to configure the IP address of the rendezvous point. So in this case, what we're going to do is there's a reason I create loopbacks, and there is a reason that I enable PIM on them. I'm going to use the loopback address as the RP address. This is just generally a smart move all around, because you can use the IP address of a physical interface. It won't stop you. But just like how just like how physical interfaces can go down, and loopbacks are going to stay up as long as the chassis stays up, just like with other features that use loopbacks to have that benefit of being independent of any particular physical transport, multicast routing with RPs is going to be much the same way. So if possible, you want to be using the loopback address here as the RP address, because in the event that one of the physical transports goes down, as long as you have some routable path to the RP, you can reroute the traffic such that it makes it the RP. The RP is really important. If the RP goes down, then you're not going to be able to bridge sources to receivers, and you're going to break your any source multicast, which is a really bad thing, which is why we want this to be a highly available service. So we're going to go ahead and configure the RP address for the loopback address. And just to confirm, it's a good idea to confirm that you can reach this address. And in this case, we can. So we're going to go ahead and do Ippmrp address, and we'll configure the IP address here. And we're going to do it on all routers. And I'm going to pop in the conf key because I don't know whether these routers are in configuration mode or not. Ippmrp address 192.168.255.4. Now you'll notice that I have run this command on R4 as well. I'm telling R4 that the RP is itself. That's an important thing. If the router doesn't know that it's functioning as an RP, then obviously it can't function as an RP. So every single multicast router in the topology, including the RP itself, has to be configured as RP address. And it seems kind of silly because when you're looking at this command, it seems like, okay, well, I'm configuring the RP address to be my own IP address. But the significance of this is that you're telling that router, you're configuring it such that it serves the RP role, because it's going to see that that IP address, that RP address, is assigned locally on one of its interfaces here. In this case, loopback 0. So it's going to assume, hey, I'm the RP, so I need to create these tunnels. And you'll see that all of the routers I've enabled the RP on create tunnels. And the purpose of these tunnels, I think I can do this here. So I can go here, and we can see here that we've got, we can look at the tunnel source and the tunnel destination. So I'll show you where the tunnel source comes from in a moment. The tunnel destination is that RP address we configured, and we can see here this is the PIM register tunnel for the RP. So this is pretty clear about what this is doing. It's the tunnel that lets you encapsulate the PIM registers that go towards the RP. So again, the PIM registers inform the RP of a new source. And on the RP itself, everyone else just creates one tunnel because they just need to perform encapsulation. But R4 actually creates two tunnels. I can do interface description. So we have two tunnels because it's the RP, one for encapsulation and one for de-encapsulation. So that's an important detail, is that the RP creates two of these tunnels while everyone else just creates one tunnel towards the RP. Now, where does the source address come from? So you'll note that if I go look at 192.168.255.4, the next hop here is going to be 10.1.3.3. This is where we're getting this tunnel source from. And the reason this is significant is because of a thing called RPF, reverse path forwarding. This is another term that we're going to have to familiarize ourselves with. So if you've done your CCMP studies, if you've done an RC, you may be familiar with something called URPF, Unicast Reverse Path Forwarding. URPF is based on, you might be able to assume, RPF. RPF is a multicast technology, and RPF exists for loop prevention. So you might assume that multicast loops are really bad, and they are. Because imagine a unicast loop, right? Unicast loop, pretty bad. But with a multicast loop, if you think about it, you're replicating the traffic. So if you have a multicast loop, you're not just looping the traffic around. Every time you loop it around, you're also replicating it again and again and again, which is a really bad thing. So we are taking extra steps to be really careful about preventing multicast loops from happening. And the way we're accomplishing this is using RPF. And RPF is a really simple mechanism. What it does, by default anyway, there are ways you can manipulate this behavior, but by default, what it does is it looks at the unicast routing table. So I'm going to run this command real quick. It looks at the unicast routing table. The RPF type is unicast, and it's learning the route from Igrp AS100. And what it does is it looks at the outgoing interface here. So the outgoing interface, if I route traffic towards 192.168.255.4, which is my RP, I'm routing it out of gig 1. So if I'm receiving traffic from the RP, I want to receive it back in on gig 1. So if this traffic loops around and hits me in behind, let's say it comes in on gig 2, for example, then we're going to drop it because that's not the RPF neighbor. And that it will essentially kill a loop because now you don't have a closed loop anymore because you have effectively killed any possibility of the traffic coming in on any other interface. You've broken the loop, you've broken the closed loop, and now you can't have traffic looping around infinitely. So again, it's a really simple mechanism. By default, what it just does is it looks at the unicast routing table for this particular route, and then it looks at this next hop, looks at the egress interface, and then it selects that egress interface and that next hop to be the RPF interface and the RPF neighbor. So gig 1 is the only interface that we're going to accept multicast traffic coming in from a tree that's rooted at 255.4, which you might remember, the RP is the root of the star G tree. And that's part of the reason why we needed this unicast topology. Because if we didn't have the unicast topology, then we wouldn't have a unicast routing table for RPF to go look at and say, okay, this is the loop-free path. And that's why, again, and that's also why it's really important that the underlying topology is loop-free. Because if it's not loop-free, then RPF is just going to assume, okay, well, the unicast topology is loop-free. And if it's not, then you're going to have a multicast loop because RPF doesn't know any better. So that's that. And the one important thing to note here, this interface for RPF has to be PIM enabled. So what I can do is I can demonstrate this. I'm going to go ahead and disable PIM here. And if I look at my unicast routing table, you can see nothing's changed, right? Just because I disable PIM, Igrp still running, Igrp still doing its own thing. We have nothing change. We have no change here. Now, if I go look at my RPF, it's going to say failed, no route exists. Now, you might look at this and say, that's a lie. That's a big old fat lie. I do have a route for this. But I don't have a route that goes over a path that's multicast capable. So what it's essentially saying here, and this is a really vague error message, is that we don't have a, it's not that no route exists, it's that no multicast capable route exists. So I'm going to re-enable Ippmrp Sparse here. And that's one thing to know about RPF. And it's a common trap. And I mentioned that now early on because we're going to run into that issue again, intentionally so, and I'll demonstrate how we get past it. We're going to run into this issue again when we cover multicast tunneling. So that's RPF. And, sorry?
You got time for a question?
Sure.
Yeah, I just noticed a few in chat.
Sure.
Well, first one, a simple one. Are you doing all this in CML? Yes, you're running all these in
Yeah.
CML, right?
Yeah. All these nodes are in CML.
Yep. And what's your terminal program?
Secure CRT.
Secure CRT. Very good.
So I have the chat open on my laptop right now.
Okay.
So I noticed that I noticed some comment about the syntax highlighting. Yeah, this is all just regex based. So there is a Cisco words.ini file online you can download if you want your terminal to look pretty with colors like this. Or you can do what I, Donald, and some others have done, just build your own list. It's all regex based, so if you can run regex here in order to highlight particular syntax. Just notice that I want to comment it.
Yeah, so if you want to do that, just do a Google search for like secure CRT syntax highlighting, and you'll find some pre-built lists you can use, or you can make your own.
Yep.
Okay, another one. You explained this, but how do you select the RP, and why did you select R4? Can you briefly just mention that again?
Sure. So again, the RP is going to be in a data path. So like I mentioned before, what the RP's role is going to be to bridge the sources and the receivers, because in any source multicast, if I have a source that's just sending traffic, it's just sending traffic to the group, it's sending it out into the wild, it doesn't know what the receivers are. The receivers have the opposite problem. The receivers don't know what the source is. So in order to solve that gap, we need a RP in the middle that's going to register all the sources and register all the receivers. So the RP is the only router in the topology that knows initially all of that information. And then when there is a source that comes online, it's going to send the traffic to the RP. The RP is going to bridge the star comma G by essentially sending that traffic down to the star comma G. What this means is that when you start sending traffic, the instant you start sending traffic, the RP is in the data path, which means that, let's say H1 is my source and H6 is my receiver. That works, right? Because R4 is just naturally in the data path for that. So with host 1 would send the traffic down. Maybe I'll launch Epicpen for this. I don't have Epicpen. What's that tool called? I have it somewhere. I haven't used it in a while. Ippmrp, that's what it is. Okay. So let's see here. So what we have is, let me make sure that my pen works. So when H1 sends traffic, it's going to send it down to R4, and then R4, let's say R7 is the receiver, it's going to send it down this way into R7. This is a logical data path. Now, let's say I made R15 my receiver. What we'd have to do is and let's say I wanted my receiver this time to be R3, or H3 rather. So I'd have to send this traffic down to R15, which would go down this path here. And then R15 would bounce it back up down to H3. This traffic path doesn't make sense, right? We are sending this traffic so much further than it has to go. Yeah. That's why RP placement is critical. So the criteria that I use to answer the second part of that question, the criteria that I use is that I want it to be in the center of the topology. I want it to be roughly equal distance between everybody, so we don't have a disproportionate impact on a particular receiver. So if I pick R4, for example, well, if I'm sending the traffic to host 3, then it would just go down this path, where R4 would send it down here, and then R4 would send it down here. Right? Fairly sensible. Or if I wanted to send it to H7, it would just have to go down this path. If I wanted to send it to H6, it would just have to go down this path. Same thing for H5, just go down this path. Get the point, right? Roughly speaking, these are all equidistant. And same thing for H4. So compared to R15 as the RP here, R15, the problem with that is that I was way off to the side over here compared to R4, which is in the center. Okay. So that's the criteria I use to select my RP. In reality, you get a lot more nuance in that, but this is a relatively simple topology. So I can just look at this and say R4 or R6, either one of them, roughly speaking, is in the center of the topology.
Okay. And one question from me. Can you configure multiple redundant RPs?
That's a topic for later. It's called Anycast RP.
Okay, got it.
Yeah. So that is coming up.
All right. And one more thing, will there be docs available at the end? Well, maybe you could give us some recommendations for studying Multicast.
I can give you some. There are a lot of Multicast resources available.
Okay.
This is meant to just be a crash course in the Multicast. I realize that I'm human and I can't cover everything there is to know about Multicast in 2 hours, 2 or 3 hours, but there are a ton of good resources for learning this content.
Okay, great. So let's go over that at the end.
Yeah, sure.
Nice.
So we've covered RPF so far. Don't think I see any questions about the RPF process. If there are any, again, like Jeremy said, just feel free to ask.
Yep.
So we've got the RP configured now. So now we can move away from PIM. For the most part, we've got PIM all settled. And we can confirm this. We have some verification commands to verify that PIM RP is properly configured. So the one that's going to show you a lot of information here is going to be show IP PIM RP mapping. And this is going to show you the RPs that are mapped for particular groups. Now, by default, all multicast RPs serve all multicast groups, and the multicast group range is 224.0.0.0/4. You can filter this, and that's why the groups line exists here. They also tell you that we assign this statically. There are dynamic ways to assign an RP. We'll cover those later. So we have this multicast group here, group range here. Again, this is 224.0.0.0 to 239.255.255.255. So this particular RP here, because we didn't configure it otherwise, is going to cover the broad spectrum of all multicast groups available. Oops, I didn't even check it off. So now that we have PIM configured, we can move away from PIM a little bit and talk about IGMP. And IGMP, in order to do that, we're going to have to bring the hosts terminal back over here. So hosts. So these are my hosts here. Now, what we're going to have to do, firstly, IP routing is enabled here, but I don't have any routes. So I'm just going to configure a default route up to my sounds like you're having fun back there. So it sounded like you dropped cups for a moment.
I think the people listening to the stream couldn't hear it. I muted on OBS, but for those of you who couldn't hear my chair, I was moving my chair around and it was very noisy.
Yep. Okay, fair enough. So I need to figure out what my next hop address is here, R11. So it should be, let me just make sure I don't boomer the next hop address here. Yep, 1211. And this should be the exact same here because they're connected to the same segment. So we'll just go ahead and configure default route up to 11. We'll configure a default route here. It should be, 0.0.0.0.0.0, 92168.3.12, I believe it is. Yep, it's 0.12. And 12168.4.13. So I dragged it off screen so I can see the topology. I'm just very quickly configuring all of the default routes here, which is real. Again, what you would have realistically for hosts, you'd have a default gateway, and having this is going to be crucial for if you understand unicast routing, hopefully obvious reasons. So we've got all these default routes configured. So if I ping 121.255.11, there we go. All right, just testing whether my default route works. So your receivers are going to be the ones that use IGMP. Your receivers and then the routers connected to those receivers. And again, as a reminder, IGMP is used for us to be able to signal multicast interest. So in layman's terms, we're telling the network that we're interested as a receiver of a particular multicast group. Now, with Cisco devices, you can, if you're just labbing and you're thinking, oh no, what am I going to use my multicast receivers? What am I going to use my sources? You know, I don't have enough money to buy Ippmrp, what for the paging multicast, whatever it may be. Don't worry. There are a ton of solutions for you to be able to add multicast. So a fairly common lab case, and it's fun to try out, is VLC. So VLC supports streaming to multicast. It supports watching streams. So if you want to lab multicast, you can deploy a bunch of VMs. You can install VLC on those VMs, and then you can test out streaming video. That is an option. If you just want to have something super simple on the host side, just so you can have multicast sources and receivers, what you can do is configure Cisco routers on their interfaces to join an IGMP group. And then on the multicast sources, if they're Cisco routers as well, you can just go ahead and ping the multicast group, and it'll just send ICMP messages to that multicast group. So in order to join a multicast group, it's a really simple process, actually. We're going to go on the interface, which is gig 00 in this case, And we're going to do IP IGMP join group. And we're going to have to specify a group address. So I'm going to use 239.1.save0.1.12.1. So this is my multicast group address. So what this does, and I'm going to go ahead and trigger a packet capture here so we can see this happening in real time. I'm going to search for IGMP. So we're going to go ahead and I'm going to, off screen here, go ahead and shut the interface down and no shut. And we should see in a little bit that we have the IGMP report message go out. And the report message is going to be the message that tells our multicast or directly connected router about our interest. In the meantime, though, I'm going to go ahead and configure the same thing here. So we have multiple receivers. Just for fun, I'm going to go ahead and change this group here. And as a reminder, you can join multiple groups here. So if I paste this in and I do a show run, you can see we have multiple groups joined on this interface. So I'm going to go ahead and remove this. So there we go. So these multicast reports, you can see by the timing, they come after multicast queries. So there's multicast queries, which or membership queries, sorry. As you might imagine, a membership query is sent out by the multicast router here, which is 11. It's sent out here, and it's basically asking, hey, is there someone who wants to join a multicast group? And these hosts here respond, well, yeah, I want to join a multicast group here, right? 2 is going to say, hey, I want to join this multicast group. 1 is going to say, hey, I want to join this multicast group. So I'm going to go ahead and do the same thing on here. So I'm going to IP IGMP join group 239.0.124.1 or 121.1. And this should be, why did that not copy? These should all be the same group address. I boomered there. One. All right. So these all need to be the same group address. I just instinctively set the last octet to be unique, but in that case, then they're part of different groups and they're not going to receive the same stream. So I need to go ahead and remove this. So all of these guys are part of the 239.0.124.1 group. Just making sure of that. Great. So we're done on the host side. Now, you can see here if I scroll down, we can take a look at this. So this is a membership report. It's really simple. IGMP version is 2. So Cisco routers default to 2. There's really no reason to run 1 anymore unless you want backwards compatibility. And if you want that, then IGMP v2 is backwards compatible with v1. But there are situations where you may need to run it. Alternatively, there's also v3. v3 is used for SSM. So if you don't need SSM, if you're just using ASM, the Any Source Multicast, v2 is fine. If you're running source-specific multicast, which we'll cover in a moment, then you'll need IGMP v3. And IGMP v3 is backwards compatible with v2 and v1. So if we go on the multicast router here, so we'll go back to the routers. So R11 is the router that's connected to our receivers. And if I do a show IP IGMP membership, you can see here we have some reporters. So more specifically, we have star, and this is going to be source agnostic. This is our source wildcard. And then we have our group here. And then we've got a reporter. So the reporter is the device that sent out the IGMP report. That's how this router is learning about the membership request. The membership report is through the reporter. The reporter here is 12.1, which is our host 1. I believe I made a mistake, and this is not source, this is channel. So if I do a show IP mroute now, you can see that we've got a star comma G here. So this is our star comma G for the 239.0.124.1 multicast group. You can see that the RP is router 4. The incoming interface is gig 1. So if we look here, gig 1 is going to be our link out to router 1. And this is, more broadly speaking, our link out to router 4. So what we're saying here effectively is that if we have incoming traffic for this multicast group, then we want to send it, then we want to be receiving it through Gigabit Ethernet 1. And this is where RPF comes back into play. Because if I do a show IP RPF for 192.168.255.4 on this router, you can see that our RPF neighbor is 10.1.11.1, which is, in this topology, router 1. That's our directly connected router on this link. So that's where we're basing this from. We're basing this off of the unicast routing table and the unicast path towards the root of the tree, which is, again, for the star comma G, the root of the tree is the RP. Now we have the oil. This is the outgoing interface list, and you can make a ton of puns with oil, I'm telling you. So the outgoing interface list
does Multicast provide lots of opportunities for puns?
Yes, it does.
Sounds good. I got to learn it.
I haven't leveraged many of those opportunities. I'm going to have to step up my game a little bit here. So the oil, if you think about multicast, remember, multicast has to be replicated because you might have multiple interfaces with interested receivers. So in this case, if we have multiple interfaces that have interested receivers, then we're going to have multiple entries in this outgoing interface list. And if we have multiple entries, what that means is that we're replicating the traffic out both gig 2 and let's say we have gig 3 here, it would replicate out gig 3 as well. So however many interfaces we have in this outgoing interface list, so the list implies, again, there can be multiple outgoing interfaces, we're going to replicate it once for every single interface. And this is, again, determined by the PIM joins. So if you have an interface that you receive a PIM join on, that indicates that there is an interested receiver somewhere down the line out that interface. So if you receive traffic for that multicast group, then you need to go ahead and add it to your outgoing interface list so that those receivers can receive the multicast traffic. Now, if I go ahead and look on R4, you can see here we have the group here. You'll notice that the incoming interface is null because we're the RP. We're the root of this tree. So we don't have any incoming interfaces here. Now, the outgoing interface list is going to be gig 1. If you think about it here, gig 1 is going to go out to this link here towards R3. And if I look on R3, R3 should also have this multicast state. It's also going to have this. The incoming interface is gig 3, which is the interface on R3 that's facing towards R1. Or R4, I'm sorry. And then we have an outgoing interface list here consisting of gigabit, let me do a show camera here, Gigabit Ethernet 1 and Gigabit Ethernet 4. So this is one of those examples where we're going to have multiple interfaces in the outgoing interface list. And the reason for that is that on R3, let's see, so we have gig 1. Gig 1 leads out to R1, so this is leading out to hosts 1 and 2. And we have gig 4. Gig 4 should be right over here. So gig 4, if you'll recall, leads out this way. It leads out to R4. If you'll recall, we also subscribed R4 to this multicast group. So when there's traffic coming in to R3 here, again, this has to go through R4. R4 bounces this back to R3. When R3 gets this multicast traffic, it's going to replicate out this interface towards H1 and H2, and it's going to replicate out this interface towards H4. So R3 knows about it, and then when it replicates this out, it'll replicate out to R1. R1 will replicate this out gig 2, which is its interface facing R11. It's gonna, and then R11 we saw had an outgoing interface list of 2, which faces these hosts. So now we have a complete multicast path. So in theory, assuming I haven't boomernating, if I go on,
that's a big assumption.
Let's say, Quit. So if I go on H5 here, and I ping towards 239.0.124.1, might take a little bit. Oh, it didn't in this case, but you can see now we've got replies back.
Nice.
So what we've got here is we've got a functioning multicast path. So we re-inspect the routing tables, the multicast routing tables. What we've got is, so I pinged from H5. H5 is going to go towards R15. That's its first hop router. So that's the first hop router in the path. If I go ahead and do a sharp PM route here, what you can see is that we've got an S comma G here. So the S comma G is for the source, specifically for the source 5.5, 239.0.124.1. Incoming interface is gig 2. So that's the incoming interface here. This is facing the source, which makes sense because this is the S comma G, so it specifically pertains to traffic from the source. So if we have traffic coming in for the multicast, we want to make sure that it's allowed to come in the interface that actually faces the source. And then the oil here is going to face towards gate 1, which is going to face towards the receivers that are this way. This is its link to R9. So let's go ahead and trace the path here. We can go look at R9, try the M route. And you can see here we've got our S comma G here. Incoming interface is gate 2, which is its interface facing R15. Outgoing interface list is going to be our gate 3 facing to R8. If we look at R8, show IPM route, we have S comma G. Incoming interface gate 2, which is facing R9. Outgoing interface gate 3, which is facing R6. Let me just make sure of that real quick. Yep, it's facing R6. So we'll go ahead and look at R6 here, show IPM route. Again, incoming interface here is going to be 3. That's the one facing R8. And then outgoing interface is going to be gig 1, which is facing towards CRP. And then we have our S comma G here. It's going to accept the traffic coming in on gig 2, which should be its interface towards R6. And outgoing interface list, gig 1. Now when it hits R3, we're going to see that we have an S comma G here. And just like with the star comma G, our outgoing interface list here is going to go towards 1 and 4, which means that traffic that is originating from 5.5 to this particular multicast group is going to go out this way. It's going to be replicated out towards H1 and H2, and it's going to be replicated towards H4. So that's our multicast path. So it seems like a lot of configuration. It's really not. So just to summarize what we've done so far. What we've done so far is we've already configured EIGRP for our unicast routing, but if not, you're going to have to get unicast routing working. So that's one of the prerequisites. But as far as the multicast goes, we configured PIM on all of our interfaces. We configured an RP, and we configured IP Igmp join group. Everything else so far has just been theory.
Yeah, it's actually quite simple, simpler than I expected.
Yeah.
I have one question. You mentioned this, but he says, if I heard him correctly, the join group command is not required on the receiver, just for the lab. So my understanding is that you're using this because you're using routers to simulate end host joining groups.
Right.
Okay.
Right.
Yeah.
So realistically, you wouldn't be doing this. Realistically, whatever application you have that's using multicast would generate the IGMP reports and then send them out. I'm using IP IGMP and join group to force the routers that I'm using to simulate end hosts to generate IGMP reports so that they can join the multicast groups. The other thing I wanted to note here is you can see here that normally when we ping, let's say we ping 5.15 here. We have just exclamation points. But here, we know a couple of things. Firstly, we're sending 1 ICMP echo. So when we ping a multicast address, we're sending 1 echo compared to 5 by default. Now, we can, of course, force this if we wanted to. We could say 239.0.124.1 repeat 2. And we can force this. And we would reply receiver reply to request 0, and then receive replies to request 1. Now, the other thing to note is that you can see here that these replies, we are not seeing exclamation points, we're seeing lists. Now, the reason behind this, more expanded form, more verbose form, is because the source of the ICMP reply was not the same as the destination of the ICMP request. So the destination of the ICMP request was this multicast address. But the one rule of multicast addresses is that both IP and MAC addresses, and what you end up doing is you map the IP addresses and the MAC addresses for multicast. I might look at that when we look at the packet captures later. What ends up happening is you are never going to source the traffic from a multicast address. Multicast addresses belong only in a destination. So because they're never going to be seen in the source is going to be the interface source of whatever the interface is here. So the interface here is 12.1. That is our source address, which means that our source address in the reply is different than the destination address here, which means that iOS is going to say, this is different. So we're going to go ahead and instead of just showing an exclamation point, we're going to say, hey, you have a reply to a request from a source address that is not the same as your destination. And I'm pointing that out to transition into this idea that multicast addresses cannot be source addresses. They are destination addresses. Because if you think about it, it doesn't make sense, right? A multicast address represents a group. So how are you going to, as one node in that group, if you're sourcing something from a multicast address, that implies that you represent the group, which doesn't make sense. So because of that, you're sourcing it from your own interface address. And yeah, so here our source address for reply was the same as our destination, therefore we got our exclamation points. So just to clarify something there. So now we've got our multicast path working. Now we can start having some fun here. Now we can start covering some of the features that are on the CCIE. So if you're just studying for your CCNP, knowing how an RP works, knowing how PIM does the signaling, and as we get further, I will debug and packet capture PIM joins and PIM registers so we can see deeper PIM operations. But now we've got this working, we can start having some fun. Because as you saw, we have our basic multicast path working, we have our RP working. So some of the issues with list topology, let's start with the RP for a second. So you'll notice I had to manually set the RP here. So if I'll show run maybe easier to show, IPPIM RP. So I had to statically set my RP address, which doesn't seem like a problem. It's just one command, but one command on a ton of routers is a ton of commands. It adds up very quickly. So ideally, you don't want to run RP address on every single every single router that comes along. You want to be able to dynamically learn the RP. It's the same argument with static routes, right? We use dynamic routing protocols like OSPF because we don't want to configure a million static routes on all of our devices. So we want to be able to dynamically learn this RP address so we don't have to put in so much legwork. And to that end, there are two protocols that we care about. And that makes three ways you can assign the RP. So I'll go back to Corel Painter here so we can demonstrate this. I'll delete this layer here and bring back this layer. So there's three ways we can assign the RP. We've looked at one of them. Three RP assignment methods. So we have static assignment. We covered the issue of that. It's static. It's much the same issue of static routes. And then we have two dynamic methods, auto RP and bootstrap router, which is more commonly referred to as Bsr. And these are, again, both dynamic methods of assigning the RP. Now, what's the difference? Remember the difference between LACP and PAGP? LACP is vendor neutral, PEGP is Cisco proprietary. Much the same way here. AutoRP is a Cisco technology. Now, Bsr is standards-based. I forget the exact RFC, but I know it's defined in an RFC somewhere. So if you care about reading the RFC, just Google for Bsr PIM RFC. I'm sure you'll find it, but I don't remember the number off the top of my head right now. So we have AutoRP and we have Bsr. Both of them have their advantages. Both of them have their disadvantages. Let's start with AutoRP for fun. So what we're going to do is we're going to remove, let me go back here. We're going to remove the PIM RP address. So we're going to go to conft, no IP PIM RP address 192.168.255.4. And eventually, we should be tearing down the PIM register tunnel that goes towards the RP because we've deconfigured it. So in a second here, when all these routers pick that up, they're going to go ahead and destroy the, it looks like they already have. We just didn't see a notification for it. So they've destroyed their tunnel towards the RP because, again, we've deconfigured it. So I do a show PIM RP map. We don't have anything. And if I try to ping the groups here, I'll do it from the source just to make sure we don't run into any issues. 239.0.124.1. You can see this dot here means that we didn't get any response back. And this is expected because now we're running up against that issue where the sources know about the group and no receivers, and the receivers know about the group and no sources. So we need an RP to resolve that. Now, I still want R4 to be my RP here. So what we're going to do is we are going to configure AutoRP. Now, AutoRP, we are going to run IPPIM, and there's two commands we worry about here. Send RP announce and send RP discovery, because there's two AutoRP roles. There's the RP itself, and then there's the RP mapping agent. The mapping agent is going to receive all of these RP announcements. So think about it like the presidential election, right? In the US, we have national committees. These national committees pick a particular presidential candidate for their party. Politics aside, this is very much similar. These RPs are, if we have multiple RPs that are sending out announcements, they're vying to be the RP. One of them has to be the winner. So the RP mapping agent is the one to decide who that winner is. And then once the RP mapping agent decides who the winner is, it advertises out to the topology, and then topology learns about it. So we have to pick a router here to be our RP mapping agent. Now, it doesn't really matter where this RP mapping agent is. It's not in the data path. So if we, in my previous example, I said that we wouldn't want to make R15 the RP, and that's true. But if we wanted to make the mapping agent R15, that wouldn't matter, because the mapping agent's sole purpose is to decide among all of the AutoRP candidates who the RP is going to be, and then send an RP out to everybody. It's not actually going to be in the data path, so it doesn't matter if it's out of the way. That being said, we're going to make it R6 just because it's closest to R4, which is our RP candidate.
Okay, so are there any best practices about which one you make it, or doesn't really matter?
Not as much as the RP, no. It really just, it's going to be much more dependent on your individual design than the RP itself is. The RP, you can say, because it's in the data path initially, we want to be really careful about that. The RP mapping agent, it's just used to elect the RP. So where specifically you place that matters a lot less than it does with the RP.
Okay, got it.
So the command on the RP is going to be send RP announce. We want to send an RP announcement, and here we can pick an interface. So this is where we start to deviate from that RP address command. RP address allows us to specify an IP address. Here we're specifying a loopback interface, or an interface of any kind. Now remember what I said earlier. We want to use a loopback because it's going to be reliable. The RP needs to be highly available, because if it's not and it goes down, then what's going to happen is new groups cannot get bridged with their sources. Things go to, things go haywire with that when that happens. So we want to set this to our loopback. That's highly available, and then we can dynamically reroute to that loopback as we need to. With auto RP, we're going to be mandated to specify. We're going to be required to specify our scope here, and this is the TTL of the RP announce packet. The RP discoverer also has a source that, or has a scope that specifies the TTL of the RP mapping agent packet. Now, in a lab, you can just set this to 255. If you want to limit the reach of your auto RP domain, this is where you would try to do that. So you would set the scope to a TTL that's lower so that the TTL runs out at by the time it hits the edge of where you want that RP domain to end. But in this lab, I want the entire topology to follow this auto RP paradigm. So I'm going to set the scope or the TTL of the packets to 255, which is the maximum. And here, we can set the interval, which is how often it's going to announce. And then we can set the group list. So this group list is going to be an ACL. This is what I was talking about earlier. So with the group list, you'll recall that I said that all RPs by default serve all multicast groups. The entire multicast range is at 224/4 range. Here, if we want to limit it such that this RP only serves this particular range of multicast groups, so I only want it to serve the multicast groups that are 229 and 230, we can set this here. In a practical sense, what we could use this to do is load sharing. So, or more accurately, load division. So we could divide up the load such that one RP takes this particular group list, the other takes another range of groups. And the RPs are only elected for a particular group range, which means that even if we have two RPs out, if they're vying for a different group range, then the RP mapping agent is perfectly happy to announce both of those RPs. It's just that when we have multiple RPs competing for the same group range, well, we can only have one. So, it's worth noting with this group list also that longest match applies. So if I have one router that's sending out 224/4 and another router sending out 224/5, longest match applies there, where any group that falls under 224/5, because the /5 is the longer match than /4, any group that falls under that 224/5 range is going to use the RP that's advertised for 224/5. All other groups will follow that same longest match rule, except because the /5 won't match, they'll default back to the RP that's advertising the /4. That's the other thing to note. That's done. So we're going to send out the RP announcement. And this isn't enough. Remember, we also need the RP mapping agent, which is going to be essentially our elector. So Ippmrp send RP discovery. This is on R6. If I can type RP discovery. Same thing here, specify an interface. This is going to be loopback 0, scope 255, and then we don't have a group list here because we're not advertising ourselves as an RP. So what you might expect to happen here is for our RP to show up, but it's not, right? We go here, show Ippmrp, auto RP here. We can see here, we've sent and received 0 RP announce and RP discovery packets. So the thing to remember here is that we have enabled sparse mode. Sparse mode requires an RP in order to do any source multicast. Now, auto RP is not baked into PIM, right? That's one thing to consider. It's not baked into PIM. Actually, we're getting some stuff here, but it's not going to spread throughout the topology. So the issue still stands that auto RP is not baked into PIM. So Bsr is baked into PIM, but auto RP uses a specific range of multicast groups in order to advertise the mapping agent and advertise the RP. Now, this is where we get in that chicken and egg problem again, because we need auto RP in order to be able to elect the RP, but we can't run auto RP without having an RP for the groups that auto RP uses, because again, when we're using any source multicast, the star comma Gs, which is what auto RP ends up using, we need the RP in order to be able to facilitate those groups. But again, chicken and egg issue. We're using AutoRP to elect an RP, but AutoRP won't work without an RP. You see where we're getting into this sort of chicken and egg problem where AutoRP is going to break because we don't have an RP, because we're using AutoRP to try to elect our RP?
Yeah.
So you remember at the beginning of the stream, you asked me whether we'd ever use dense mode. And I responded mostly no, except in one scenario, this scenario. Because using sparse mode to elect our RP with AutoRP is impossible. We cannot use AutoRP here. Or I'm sorry, we cannot use purely sparse mode here. There's two ways we can fix this. We can, and by the way, switching to purely dense mode would not be a solution, because if we switch to a dense mode implementation, then we wouldn't need an RP. Dense mode doesn't use an RP. So if we want to keep with sparse mode and we want to keep with using AutoRP to elect our RP, we've got two options. We can use that sparse dense mode command that I mentioned earlier. That sparse dense mode command, if you'll recall, is going to run sparse mode primarily, but for any groups where sparse mode fails to signal the multicast group, we're going to fall back to dense mode. This is one of those scenarios. The AutoRP groups are going to fail using sparse mode. We can use sparse dense mode to fall back to dense mode for the AutoRP, and then just use sparse mode for everywhere else where we can. The other solution, and the problem with this, is that sparse dense mode is going to fall back to dense mode for any group where we don't have an RP, which, depending on your design, may or may not be a problem. Maybe we just want to use dense mode for our auto RP. And for anything else that we don't have an RP for, well, you know what, screw it, right? We don't want to use dense mode anywhere except our auto RP deployment. There's a command for that, Ippmrp auto RP listener. So if we run this command on all of our routers, so Ippmrp auto RP listener, what this does is it's going to do essentially the same thing as sparse dense mode, except it's only going to fall back to dense mode in the context of our auto RP multicast scripts. So in a moment here, and it takes auto RP a little bit to converge. So we go ahead and do this here. You can see we've received 0 RP, 0 auto RP messages. So we're going to go ahead and have to wait for auto RP to converge here. But in the meantime, are there any questions?
Don't see any new ones.
Okie doke.
Yep. I got a question for me. When will the course end? End of this year, so end of this month. Getting close.
Nice. Yeah, how many videos left? You got 6 or something?
Yeah, on YouTube, maybe 6-ish. In total, I have to make 2 more, and then I'm done.
Ah, fair enough. Nice.
Yeah.
Congratulations.
Taken over 2 years. Oh, we got a comment here. I've seen a few cases where Igmp is enabled on switches, but seem to not transmit it to the TV setup boxes. I usually reset or send the customer a new switch. Did the Igmp break? You following that?
Probably not enough information to tell there. Yeah.
Okay.
Yeah. So they probably need a little more information there in order to be able to pinpoint the exact issue there. But going back to this, we've got our tunnel up now. So if I do a show Ippmrp mapping, that's our verification for our RP. Now you can see we've got our RP, which is 192.168.255.4. The info source, which is where we're learning this information from, is router 6, which is our RP mapping agent. And this is elected via auto RP. So if we go back here, and I try to ping our multicast group again, we can see that we have reachability again, because now we have an RP. So now we have an RP here. Our RP is 239.0.124. Whoops, let me go to R11. So show IP mroute 239.0.124.1. So we have our what's it called? Our Sarcoma G here, which is our RP. rooted RP rather, and then we have our S comma G, and this is H6, which is the source that I was sourcing the multicast traffic from. So I'm sourcing it from host 6. So you'll notice I only had to run one command, Ippmrp auto RP listener. And then all of these routers dynamically learn their RP. What that means is if for whatever reason I need to change GRP, let's say R4 fails, I need to take it out of service, whatever the case may be, I can just run the send RP announce command on another router, and it's going to go ahead and send out the RP announcement. The RP mapping agent is going to do its thing, and then all of the other multicast routers are going to learn the new RP. The other thing I want to note is we can see here 224.0.1.39 and 0.1.40. We can see the D flag here. D, if we look up here, is you might be able against dense mode. So these are dense mode trees. And again, remember, dense mode, we're assuming that everyone is interested, which since this is just auto RP, it's fine for us to be running dense mode for these particular trees, mostly because we don't have a choice with auto RP. So we can see that 224.0.1.39 is a dense mode tree, and 224.0.1.40 is also a dense mode tree. And more specifically, list is going to be the group where the RP candidates announce. 40 is going to be the group where the mapping agents do their work. So we can see here that we've got 224.0.1.40 is joined on loopback 0. So what we're doing here essentially is we are listening to the sources, which is going to be 6, which is the RP mapping agent on 224.0.1.40. And that's where the mapping agent is going to be sending the messages regarding the RPs. And that's how the rest of the topology learns about this. So the key point here is that we need dense mode because auto RP is just plopped on top of PIM. It's literally just acting like an AR multicast traffic, except because we don't have an RP, we can't run sparse mode because we're trying to use auto RP to elect an RP, to elect an RP. So we need to switch this back to dense mode. But again, remember, there's 2 methods you can solve this. I used one of them in IP PIM auto RP listener to enable this. And then the other way was to go down to the interface level and enable sparse dense mode. Either of those solutions would have worked. Sparse dense mode would have been a lot more broad in its dense mode fallback capabilities than auto RP listener. So it really just depends on what you want. So that's auto RP. Any questions about auto RP?
Nope, nothing at the moment. Cool. Again, everyone watching, feel free to ask questions if you're not sure about anything.
All right, so that's auto RP. So all that work, and we're going to tear it down. I say all that work, it's literally just one command: send RP announce, loopback 0, and on R6 we're going to do a no IP PIM send RP discover L0. And now we're going to go ahead and go back and do a Bsr implementation. So Bsr is the one that's more interesting because Bsr is baked directly into PIM. It's a PIM standard. So it integrates directly into PIM messages instead of something auto RP, which is going to just run its own multicast group. So we have 2 roles in Bsr, just like we do with auto RP. We have the Bsr, which roughly translates to the mapping agent. And then we've got the RP candidate, which of course is the same thing as our send RP announce here. So the 2, in terms of roles, the 2 protocols are pretty analogous. So on R6, we're going to be using that as a Bsr because it serves the same role as a mapping agent. And then R4 is obviously going to be our RP candidate. So the command here, the commands rather, we have a Bsr candidate for the bootstrap router. This is what Bsr stands for, bootstrap router for our mapping agent. And then we have the RP candidate, and this is going to be our Bsr RP candidate. So it's the same command structure. We're still specifying an interface here, loopback 0. We don't have to specify a scope. So that's one difference in the commands here. You can just enter here. But the thing I wanted to point out is priority. So this is one big advantage of Bsr compared to AutoRP. AutoRP does not let you specify priority. So if you have multiple RPs that are vying for the same groups, then the way that the mapping agent decides is going to be highest IP address. There's no way you can change that. Or it might be lowest, I don't remember which, but it's based on the IP address of the announcement.
That's kind of surprising that there is no priority.
Yeah, yeah, same. I was quite surprised when I learned about that too. Now, there is a way you can manipulate it, and that is through longest match. So if you needed to manipulate it, you can use that group list function in that RP announcement in order to give the RP that you want to use the longest match. And in that case, both of them would end up being sent out by the mapping agent, but the preferred RP would be used by nature of longest match. Bsr has a much cleaner approach. You can see it has RP candidate priority. So we can, if we wanted to, if we had multiple RPs, we can say, hey, this is the priority value that I want. And so this helps our redundancy. If I wanted to advertise multiple RPs, because again, this has to be a highly available service, and if I wanted to advertise multiple RPs for redundancy, this way I could. But I'm not going to mess around with priority because I just have one RP here for now. And then here, we're going to run Ippmrp Bsr candidate, loopback 0, and list hash mask length for RP selection. This ties into the Bsr algorithm. It's a bit deep in the weeds. I'm not going to cover it in the stream. I think INE has a good article on it from like years ago by, I think it was Peter Lupukov last time I saw. They have a good article that explains the hashing algorithm for selecting RP from a Bsr perspective. Again, not going to cover that. It's a little bit deep into the weeds. I'm just going to cover the basics of Bsr. So with our Bsr candidate, you can see we have our tunnel coming up again. And here, if I do a sharp Ippmrp map, you can see this was very fast. We have our info source, and it's via bootstrap. So if we see via bootstrap, we can conclude that the RP was learned via Bsr. So much the same way, I'm going to go on our H7 this time, and I'll ping a multicast group, 239.0.124.1. Show IP interface brief. Oh, because I haven't configured. Nice. 192.168.7.7. Let me just make sure. Cool. So 209.0.124.1. There we go. See, I did boom or something.
You got to get at least one per stream.
Yeah, Donald will be proud. So we've got this working now because we've got our RP and we have elected our RP via Bsr. So we're running a little low on time. That's okay. I think we've covered a lot here. I'm going to cover a couple more things, and then I guess we can call the stream a wrap.
Yeah, sure. Sounds good.
So probably my the items that I have left on the agenda here would be Anycast RP, which ties into the RP redundancy thing that you asked about. And we can take a look at SSM and BIDR. And then from there, we can wrap it up with, and I don't think there's any more features I want to cover. We can wrap it up with packet capture. So we can take a few minutes, look at the packets that PIM and Igmp send out, inspect them, and see how they work. And then we'll maybe run a few debugs to wrap it up.
Sure. Sounds
so all with our RP dynamic election methods. So that would be AutoRP and Bsr. The thing is that, take a look at this expiration timer. This is 2 minutes and 17 seconds. So if R4 just straight up went down, I went on the loopback interface and I shut this down, or I went here and I straight up just took it out as an RP candidate. That wasn't the plan. Let's see. Here's a better way. Here's a better way. I'm gonna go ahead and, if it wants to do that, I'll let it re-elect the RP. And then I'm going to just shut down the physical interfaces. So this would simulate, okay, good. So this would simulate something like a router failing in production outright. So if this happened, Bsr can't pick it up. And what this means is that we're gonna have to let the expiration timer run down. The expiration timer in this case is 2 minutes and 11 seconds. What this means is that for the next 2 minutes and 11 seconds, or now, and it was triggered by, I think, the PIM neighborship going down on the other side because the whole timer expired. So, actually, no, never mind, it's still there. So the point is, for the next minute and 45 seconds, and the timer is going to keep ticking, we think that the RP is still up when it's not, which means that we're not going to try to re-elect another RP. Let's say that there is another RP. I configured R7 or R8 or whatever the case may be. I configured another RP to be an RP candidate. Even if I did that, for the next minute and 17 seconds, there would not be another RP election by this Bsr. It would not send out another RP. For the next minute and 17 seconds, and as far as I've been talking, this has been the RP, even though it's been down, you're not going to be able to form any multicast groups. You're not going to be able to bridge the source and the receivers for any new multicast groups. The old multicast groups that already are bridged, they're going to work. But for another 51 seconds, new groups are not going to be able to form, which is problematic. Auto RP is worse. Auto RP is 3 minutes. This is, I think, 2 minutes and a half. So this isn't so bad. Auto RP is 3 whole minutes, 180 seconds, which is terrible convergence time. 3 minutes in the IT world is an eternity.
Yeah.
So we want to be able to converge faster. There's a couple of ways we could probably do that, right? But the best way is to take RP convergence out of the hands of the Bsr. So remember, what the Bsr is advertising is not the route, strictly speaking, it's not the router that's the RP. It's advertising an RP address. It's doing what we did with the Ippmrp RP address command dynamically. So it's not saying, hey, router 4 is the RP. It's saying, hey, this is the IP address of the RP. Send your PIM joins for the star comma G to that address. Now, it just naturally happens in this simple example that the two are pretty much synonymous, right? That sending out the RP address is the same thing as saying router 4 is the RP. In this very, very simple example. But because it's just advertising an RP address, that gives us a lot of potential. And that potential comes in the form of Anycast RP. Now, keep in mind, Anycast RP works for anything but bidirectional PIM. So bidirectional PIM, there's another RP redundancy strategy called Phantom RP. And I may or may not have time to cover that. But if not, there's some pretty good documentation on it. It's basically just an exploitation. I should really boost my eraser size here. There we go. So Phantom RP is really just an exploitation of the longest match rule. You're on the loopbacks where you're advertising the RP, you're basically setting different subnet masks such that when the IGP advertises it out, the route that you're preferring is going to be the longest match, which means the one of the most specific subnet mask. So you would give your most preferred RP the most specific subnet mask so that the other routers will prefer it. But in other implementations, we can use Anycast RP. So as a reminder, Anycast is one to nearest, right? It's not traditionally wrapped into unique brass, broadcast, or multicast. It's Anycast, which is not a specific type of traffic. It's a routing paradigm. So what we're going to do with Anycast is we're going to take two routers. In this case, it's going to be our 2 or 3 or 4, however many RPs. We're going to advertise the same address. And the way we're going to do that is we're going to configure a loopback address that has the same IP address across all of those routers. And we're going to push it into IGP. That has the effect of, because IGP isn't going to say, these are 4 different interfaces. What it's going to think is, I have 4 paths to the same network. And when you have multiple paths to the same network, well, Anycast or not, it's just a metric calculation. It's just a decision based on the routing metric. So that's how you achieve one to nearest routing, because you could have a router on one side and a router on the other side advertising the same network. The ones that are closer to the respective routers are going to use that path because, again, EIGRP or OSPF or whatever isn't going to see it as 2 separate networks. They're going to see it as the same network with 2 paths. So we can leverage Anycast, because the thing with Anycast RP is that the conversions is taken out of the hands of AutoRP. It's taken out of the hands of Bsr. So we're not using any of that to do convergence. We're going to use the IGP itself to do convergence. Because think about it, if your RP goes down and you're running Anycast RP, so let's say we've got the topology here. So I'll just draw a sample topology here that should make this a little more visible. And then, sure. So we're going to say that both of these here are going to be our RPs. And they're advertising the same, let's say 1.1.1.1. Right? So actually, hold on, this link here kind of ruins it. Let me remove this link real quick. And let me see. I'll remove this link real quick. And I'll remove this link. Whoops, I can't do that. Okay, I'll keep it that way. Let's say I boost the metric here to 10, and let's say we keep the metric here 1. Okay, so what's going to happen is 1 here is going to, again, remember, so these are both loopbacks that are advertised into IGP. So these other routers here get that IGP advertisement. And what's going to happen is R1's going to select R3 as its as the path that it's going to use to get to this network, 1.1.1/32, because it's the closest IGP-wise. So we're assuming that all these links have a metric of 1, except the one that I manually artificially boosted. And then R4 is going to choose R2. So R1 and R4 are going to choose completely different RPs. And in fact, I'm going to redraw something here, so I'm going to need it in a second. So R1 and R4, completely different RPs. And that means that if, let's say, R3 goes down, right? And that means I do need to sync back. And I'm going to just have to boost the metric here. So R3 dies. Someone cuts the cable, whatever the case may be, R3 dies. Instead of waiting the 3 minutes for auto RP to converge, R1 and R2, what's going to happen is the IGP is going to converge, right? You're going to lose the advertisement from R3 for the 1.1.1.1 network, and that means that R1 has no better path to 1.1.1.1 than through this link right here. So it's going to end up switching to using R2 as the RP, but not because it received a new RP election message, not because it knows that it selected a different RP, but because the underlying routing topology underneath multicast changed so that any traffic directed to 1.1.1.1, instead of being directed to 3, was directed to 2. Because, again, the IGP converged, right? So the formal term for this is we're making the RP convergence a function of the IGP. And IGPs are really good at converging. As you might imagine, that might be important for their daily function. And with IGPs, we're going to integrate things like BFD to make this process faster. and to bring the neighborships down faster so that we can, by extension, achieve the database convergence quicker. We can integrate various optimizations to make sure that convergence happens quicker. We can implement things like FRR if we need to. So we can get this to sub-second convergence, which is a lot better than the 2.5 to 3 minute convergence that we saw with AutoRP and Bsr.
Yeah, just a little bit better.
Just a tiny bit better. So what we're going to do is we're going to move back over here. Now, in order to do Anycast RP, I'm going to need 2 RPs. This is where RP redundancy comes in. So I'm going to go back to my CML. And we're going to pick 2 RPs here. So we're going to pick 4 and 5 as our RPs, let's say. So now what we're going to go ahead and do, actually, no, I'm going to pick 3 and 4 as my RPs. Because 5 is, relatively speaking, more out of the way here. 3 is central. So I'm using that same criteria that I used earlier for picking the RP, except I'm bringing it back around to R3 and R4. So now what I'm going to do is create a new loopback 1. So in order to do Anycast, I need the Anycast IP. Let's make the Anycast IP 3.4.3.4. And again, I need the exact same network. I cannot change the subnet mask. I have to use the exact same network address and the exact same subnet mask because, again, I'm relying on the fact that the IGP is just going to think that these are 2 different paths to the exact same network. And then I'm going to go ahead and advertise this in the edge RP. So I'm going to go ahead and do this. Router edge RP 100, paste this in. So now if we go to show up your route on router 1, we have 3434. And if I trace route to 3434, we're going to source it from our loopback 0 interface. You can see that now we're going to 3. But if I go on, let's say, R14 and I trace route, what's going to happen? Source back 0 numeric. Let's see. Let's hope we got that on the table. Fun. Let's see. Are we advertising it over here? We are. R6. R6 on the beginning here. Do we have an adjacency here? Ah, that's why. I shut down the interfaces, this RP. That will explain it. To simulate the failover. That's right. And you can see that eventually the tunnel did go down on these routers here. So up here, eventually the interface or the tunnel did go down, but that took a while.
Yeah.
So I think I'm still running Bsr here, or not Bsr, RP. So I think I might need to strip. Yeah, I need to strip this command. I need to strip this command out because it's going to interfere with what we're doing here. System Bsr. I can leave the Bsr as is. Okay. So now if we go ahead and do a shuffle route here, okay, we've got it. So now it's going to 4. So you can see simultaneously on this side of the network, because R3 is the closest, because it would have to traverse R3 to get to R4, R3 is the closest, therefore this side wants to use, and down here as well, because it has to go up this way, this side is going to want to use R3. Everyone on this side is going to use R4. So we've got, roughly speaking, an even split here. So along with redundancy, Anycast RP can do the same thing as any Anycast service can, which is because we're doing this based on metrics, we're doing one to nearest, we can also do load sharing because different routers are going to be nearer to different RPs based on their location and the topology. So now instead of having one RP bear all the load, we've got 2 RPs bearing the load, which means that along with redundancy, we're also achieving load sharing, which is an added benefit here. So it's a 2-for-1 deal. So we've got the Anycast set up now. Now we need to set up the RP advertisement. Now, The important part is I'm going to go ahead and enable PIM on this Loopback 1 interface as well. So with Loopback 1, we've enabled IPPIM Sparse. That's this new Anycast interface. And we can use any of the 3 methods from before to signal our RP. We can statically set the RP address to be this new Anycast address. That would work. Or we could combine this with the dynamic RP assignment method that we used before. We can use AutoRP or we can use Bsr, either or. And the implementation does not change. All that changes is the fact that we're using this Anycast address to advertise the RP announcements instead of using the unique loopback on every single route, right? So here we already have Bsr set up. I already have this Bsr candidate set up, so I'm just going to use Bsr again. Although again, any of the 3 would work. Depends on your application. So IPPIM RP candidate loopback 1 this time. And it doesn't really matter the priority here. And I'm going to do the exact same thing on, did I do it on 4? Yeah, so I'm going to do it on R3 too. IPPIM RP candidate loopback 0, or loopback 1 rather. That's it. So now we have to do it on both because again, this RP candidate command tells this router that we are acting as our RP. So that being said, let's go ahead and solve one last issue. So we have one remaining issue, and you can see here when we do our show IPPIM RP map, I can't talk. Show IPPIM RP map, we have our candidate RP disclaimer here, so we can see that we are a candidate RP. One thing that we're going to have to solve here is a split brain issue. So if you have dealt with clusters, then you know the pain that it can be in order to get 2 independent chassis to coordinate with each other. If you don't coordinate them, then you can run into a split brain because both of these RPs right now are operating completely independently. So if we have PIM joins for the or star comma Gs are going up to the RP, this side is going to send it to R3. This side is going to send it to R4. That's an issue. As well as that, if we have sources that are going to send PIM registers, the first hop routers rather, that are connected to the sources, they're going to send PIM registers. Again, they're going to send them up to the RP. But the definition of where the RP is, which router is the RP, is different depending on your location in the network. And these guys are not coordinating anything, which means that their multicast routing tables are completely independent. And as a result, you have this split brain scenario where each router, again, is operating independently. So we need some way to coordinate between these 2 routers such that we can advertise more specifically, the source messages, because we care about the S comma Gs. We don't really care about the star comma Gs. The star comma Gs can be different. But what we need to advertise over is the S comma Gs, because we need both RPs to simultaneously know when a new source has come on. These RPs can have independent star comma Gs if they want, right? Because the star comma Gs just signify receivers. And like I mentioned earlier, we are load sharing this. So R3 is covering this side's receivers, R4 is sharing or covering this side's receivers. So we don't care about the star comma Gs. We care about coordinating the S comma Gs. And the protocol that we're going to use for this is called MSDP. And it's funny because this is how the stream originated. Jeremy and I were bantering about MSDP, and that's where the idea of having a multicast stream came from. So now we're finally getting to cover MSDP.
There we go. I've been waiting for this moment.
Yeah. So MSDP is the Multicast Source Discovery Protocol. There's 2 uses for MSDP, 2 main uses. There's lists, and then there's inter-domain multicast. So what we've been covering right now is intra-domain multicast. Intra-domain multicast is what we get when we have all of the multicast under one central administration. But what if we were coordinating multicast with another organization and they had their own RP? Well, if they had their own RP and we had our own RP, and we have separate domains here, then fundamentally, if you break it down, we're running into the exact same issue there with inter-domain multicast as we are here. Here, we've got two separate RPs that are running independently that have their own domains. So if you break it down, it sounds different because it's used in a different context, but inter-domain multicast and Anycast RP suffer the exact same split brain issue, which means that we can use the exact same tool to solve them, which is MSDP. MSDP is dead simple to configure, and it's also dead simple in its operation. So the way you configure MSDP is IP MSDP peer. You specify the peer address. You can also specify the host name, which is going to do DNS resolution. So you can, so in this case, we're going to specify the loopback 0 addresses. So we're not going to specify the Anycast addresses, because if I were to specify the Anycast address on R3, for example, it would assume that we're talking about R3. So we need, this is an out-of-band peering. We need something that's separate from the Anycast RP that we can use to exchange these S, Gs. So we're going to do IPMSDB peer, and then the loopback 0 address of the other RP, which is R4. And we can specify our connect source. This is our source interface. So I'm going to specify loopback 0. There is a remote AS here. This is purely cosmetic. This has no impact on functionality. So if you want to configure remote AS, this is more intended for, like I mentioned earlier, inter-domain multicast, where we can use this remote AS functionality to keep things organized and make sure that we are straight about what peer belongs in what AS. But again, it's just purely cosmetic. If I just don't configure remote AS, it's not going to yell at me. Nothing's going to happen. The world won't burn down. So now I've got one side configured. I need to configure the other side. IPMSDB peer, 192.168.253, connect source, loopback 0. And that's it. That's our MSDP. Now, MSDP test does take a little while to come up. It will come up eventually, but it takes a little while to come up. It takes a good few seconds there. So while we're waiting, any comments or questions I need to address?
Since the previous one, well, we have a comment that someone would like to see Igmp snooping, but not sure if we have time for that.
Igmp snooping, Igmp snooping is a fairly simple concept. I can explain it near the end. The problem is that if I were to demonstrate Igmp snooping, I would be using switches, iOSVL2. And as far as I can tell, iOSVL2, it will let you configure Igmp snooping. It won't let you configure PIM snooping, which is something different, but it will let you configure Igmp snooping. But as far as I can tell, it doesn't actually work. So you can configure Igmp snooping all day, but as far as I've seen, the actual data plane forwarding functionality that Igmp snooping is meant to create doesn't work in the virtual switching platform, which is why I have elected not to demonstrate it here. But I can talk about it near the end if he wants to see it.
Okay,
it's
sure.
just probably a 5-minute discussion there.
Yeah. And we have another question. I'm not sure what he means. DJ Cloud Pakistan, you'll have to specify. He asks, which type of application are you using? Maybe referring to CML for the lab. He's using CML, Cisco Modeling Labs.
Yeah, there's Secure CRT for the terminal.
Yeah.
And then if you're referring to the actual multicast application, not applicable. I'm just pinging with ICMP to the Multicast Group in order to simulate a stream.
Right.
Okay, so like I said, does take a good few seconds to come up, but while we were talking, the MSDP peer did come up. So I can do a show IPMSDP peer, and you can see here that we've got peer 121.2554. Again, AS question mark. We don't really care. That's just cosmetic. So if you did configure remote AS, this is where you would see it. The state is up. And we could do a filter. So this is what this is. So we can filter the SA messages, which is the source active messages. The SAs learned from the peer are 0. So let's talk about SAs for a second. So SA messages are source active messages. So you'll recall that I said that we don't care about the star comma Gs being coordinated because Again, each of those RPs manages its own domain in a sense, but we do care about the S, Gs, because if there's a source in the other domain, then we want that source's traffic to make it into the other domain. In order for that to happen, both of the RPs have to be aware that there is a source. This is where the source active message comes in. So when an RP detects that there's an S, G that's being created, and the S, G, as a reminder, is created by the PIM register message that the first hop router connected to the source sends up to the RP. When this S, G route is created, what happens is this RP is going to recognize that, hey, I have to create the SA message and then send it out to the other RP. So what I'm going to do is I'm going to have to do a new multicast group for this, because right now, as I see it, I think everyone's using the same RP in this group that we have. 1, 2, and 4 are both using 3 as their RP, so I need to change this a bit. So what I'm going to do to demonstrate this is I'm going to, see, I'm looking at my CML right now to figure out what we can do. I'm going to make a new group, Igmp join group. I'm going to create a group with 1, 3, and 6. So 239.0.1, 3, and 6, and then 1. So I'm going to take this command, copy paste it here and here. So what's going to happen is we can demonstrate this actually. And again, you can see if I do a show Ippmrp map, you can see that we have the Anycast address here. And if we do show Ippmrp map on every single router, this output is going to be the same. But we know that not every single router in the topology is using the exact same router as the RP. Some of them are using R3, some of them are using R4. But it doesn't matter, because Bsr is just advertising 3.4.3.4, and then we're relying on the underlying unicast topology in order to direct that traffic to the nearest RP. So we go ahead and look at show mroute for 224 or 239.0.136.1, I think the group is. There we go. So we have the outgoing interface list here is 1 and 2. 1 and 2. If we look at 1, 1's going to go out to gig 1 on R3 is going to go out towards H1. Gig 2 on R3 is going to go out towards H3. Now, if we go on R4, and notably, I want to highlight this. Notably, R3 does not have in its oil gig 3, which would go out towards R6 or H6. And the reason for that is, again, because H6 is using R4 as its RP. So the PIM join that R15 sends up as a result of the Igmp report, sent from H6 to R15, that gets sent to R4, and R4 records it in its star commentary, and it doesn't get sent on to R3. Now, we can say the same story in reverse for R4, which is our second RP, 239.0.136.1. So you can see here we just have one interface in the oil, and you might be able to guess that interface is gig 2, and gig 2 goes out towards R6. So R4 is not aware of any of the receivers that are happening over here. But that doesn't matter, remember, because these RPs are serving different domains. So we don't care if they coordinate the receivers, because their receivers are their responsibility. What we care about is that both RPs know when to start bridging the source traffic to the star commentary so that the receivers can receive it. So what we can do here is we're going to go on H2. So H2 is our source. And we're going to go ahead, and for this, I'm going to make this interesting. I'm going to start a debug. H2 is connected to R11. So debug IP PIM is going to be our debug. Debug IP, what else do I want to do? mrouting. There we go. Debug IP mrouting. So we're going to look at R11, and I'm going to start my ping to 239.0.136.1. Now, what you'll see here is this is going to start going crazy. So what we have is we are adding the register encapsulation tunnel of tunnel 0 as a forwarding interface of this S comma G. So this is the S comma G where we have 2 as the source and 239.0.136.1 as the group. It's going a little bit crazy right now. So what we're doing is we're setting the F flag, T flag. I'll go over that in a moment. We're building the join packet here, and then we are we're sending it out, but I don't think it specifically says here that send it out. So we're sending this out towards gig1 because if we look at the RPF neighbor, so remember we're interested in what the RP is. The RP is 3434. The RPF neighbor for 3434 is, you guessed it, 10.1.11.1. So we're sending the register here towards 10.1.11.1. And if we look at R1 here, 239.0.136.1, we can see that it's aware now of this this S comma G. We saw that the F flag and the T flag were set. The F flag is the register flag. That's fairly self-explanatory. It's the flag that you set when you're sending a register message. And then we've got the T flag here. The T flag is the SPT bit. We'll cover that closer to the end because that covers the SPT switchover, and that's probably what I'm going to end on. Besides some miscellaneous things like Gmp Snooping, just to tie up some loose ends. So we have this S comma G here, and this S comma G is going to go towards gig 1. Gig 1, whoops, not that. This gig 1 here is going to go towards R3, which is our RP. So if I do a Sharpie M route for 239.0.136.1, we know about the source. Now, here we're going to see the A bit. The A bit is a candidate for MSDP advertisement. So this router recognizes that A, I have an MSDP peer. B, I have an S comma G. And this is a candidate, therefore, to be advertised to my MSDP peer as a source active message. So what's going to happen here is we can see that the outgoing interface list is gig 3 and gig 2. Gig 3 goes towards R4 because if R4 is going to send the source traffic to the other multicast receivers in its domain, it needs to receive that source traffic in the first place. And so R3 is responsible for sending that multicast source traffic towards R4, and it does so because it's an MSDP peer. Also, we have gig 2, which is this interface here going back out towards R2. And this is so we can get to H3, because remember the subscribers of this group are 1, 3, and 6. And R3 is responsible for getting it to H3 and to H6. So this is the reasoning behind our outgoing interface list. And now if I go ahead and do a Sharpie M route for 239.0.136.1, previously we just had the star comma G. And in theory, soon enough, we should have, maybe it expired. Yeah, it expired. Okay, let me go ahead and resend the traffic. So the S comma G's do expire. So that is one thing to keep in mind. They're not going to stick around forever. It's like an IPsec tunnel, where you're only sticking around if there's interesting traffic. If there's not, then you're going to tear the tunnel down. So we need to go back and resend the traffic so it re-triggers and I pinged it from H2. Okay, so let's go ahead and look here. And soon enough, show IP mroute 239.0.136.1. Okay, cool. So now we have this S comma G here. So now the S comma G is present both on the mroute table of R3 and the mroute table of R4. And now that we have it in the mroute table of R4, we can see the incoming interface is gig 1 and the RPF neighbor is 10.343, because the route from R4's perspective is R3. That's the other RP. And the outgoing interface list is gig 2, because remember, gig 2 is the outgoing interface list for our star comma G. Remember, we're just bridging these. And we can see we have a flag M here. So A was the flag for this router because this router learned the S comma G through a pin register. And then it advertised this, it's a candidate to be advertised via MSDP. R4 only knows about the S comma G here because of MSDP. So it's using the flag M instead, which is an entry that was created using MSDP. And now we can see here in the H2 output, 1, 6, and 3 are responding. So we have this working now. And again, just like most of what we've been doing here, this was relatively very simple to configure. We had to create a loopback that was an Anycast loopback, meaning that we assign the same IP address on both routers. We advertised in the IGP. We configured the appropriate RP assignment method, whether it be Bsr or auto RP or static RP address. And then we configured MSDP between the RPs. 4 configuration commands. What's difficult is understanding a theory behind what we're doing and how we're doing it and why we're doing it. So, with that being said, that's probably all the time that I have here. I do want to cover 2 more things, though. Firstly, I want to cover the SPT switchover. I'm not going to demonstrate it, I don't think. And the second thing is I do want to at least take a look at some packet captures. Even if I'm not capturing it, I may just steal some of Network Lessons' publicly accessible. Or no, I'll packet capture it. Why not? Okay, so yeah, I'll packet capture it. So the theory behind the SPT switchover is that we don't, once we bridge the S comma G and the star comma G, we don't want to keep sending stuff on the star comma G. Because remember, all the RP exists to do is to teach the receivers about the source and to teach the sources about the receivers. That's all we want to do. Now, when that happens, when the receivers learn about the sources, we initiate a process called the SPT switchover, which is the source path tree. So there's 2 types of trees. We have the RPT, which is the rendezvous point tree. You sometimes hear us call it the shared tree. And then there's also the SPT, which is the source path tree. Here is called the source tree. So you have shared tree, source tree, SPT, RPT. Different letters, same concept. Now, roughly speaking, these map pretty cleanly. Well, not pretty cleanly. They map to star comma G and S comma G. So formally, a star comma G is a representation of the RPT. So we talked about how the star comma G tree was rooted at the RP. This is the rendezvous point tree. It's the shared tree. The S comma G is the route that represents, or the multicast state that represents the SPT. And this is the source tree. And you can imagine why this might be called the source tree, because this is rooted at the source. Is rooted at the source. This is rooted at the rendezvous point. Now, when the rendezvous point is, let's say it's out the path, right? Let's say we picked R15, right? So when the traffic starts to flow between the S comma G and the star comma G, when the source's traffic starts to get to the receivers because the RP has now bridged them, it's forwarding it, the last hop router, so in the context of our path, the first hop router is that router connected to the source. The last hop router is the router connected to the receivers. The last hop router is going to see, hey, I know the source now. So previously, the issue was the LHRs, the last hop routers, did not know what the sources were. Well, now it does, because it's receiving the traffic from the source. So now I can say, okay, I want to do an SPT join. I want to join the SPT. because I don't necessarily want the traffic to keep flowing to a rendezvous point. I want the most efficient path to the S, G, because now we have a source, right? We don't need the RP anymore necessarily. That's why when the RP goes down, we don't lose the existing groups by default until they expire, because the receiving routers, the LHRs, will have joined to the SPT. Meaning that, and the SPT isn't reliant on the RP, because the SPT is not rooted at the RP, is rooted at the source. It's rooted at more specifically, the FHR, the first hop router. So we don't need this RP anymore. Preferably, we want to get the RP out of the way as fast as possible if it's not actually the data path. So that's why I meant in the beginning of the video, I mentioned how the RP is in the data path initially. Because when the traffic is first flowing, that's what it is. It's in the path initially. But when the SPT switchover happens, let's say that I did happen to pick R15 as my RP, right? Initially, the traffic flow would be very inefficient. Let's say that R1 was my source, and we've got R3 and R5 and R7 as our receivers, right? So initially, the traffic would have to flow towards the RP. So in this case, it would go something like this here. And then it would go down this way, it would go down this way, and then it would go down this way. So it would take the long path. But when this router, which is the LHR, when this router, which is the LHR, and when this router, which is the LHR, so 11, 12, and 14 are all LHRs. When these last hop routers are connected to your receivers, receive the source, the traffic from the source, it realizes that, hey, we know what the source is now. The RP has done its job. It has bridged the source, and the receiver has closed the gap. Well, now we know what the source is. We can join directly to the SPT. We can join directly to the shortest path tree. So it sends an S, G PIM join. So that's what I was talking about earlier. I think we saw it earlier. It was sending a PIM join for the S, G. That's what's happening here. The LHR are sending PIM join to the S, G. What's going to happen, therefore, is that the multicast traffic is going to flow directly down the S, G, right? Because it's coming from this particular source, which is H1 in this case. It's going to flow down the source tree that's rooted at the source. So now we're not looking at the IGP path towards the RP. We're looking at the IGP path towards the source. Now, for H5, for example, R15 is still in the path. But for H7 and for H3, R15 is not in the path. So R15 gets pruned out as far as that goes. And if, in theory, let's say that H5 wasn't using R15, let's say that I had a direct connection to R9, for example. So we add a new link from here to R9. Maybe it's easier to use a different color instead. So we use white. We're adding a new link from H5 to R9. Well, now the shortest path to the source, which is over here, is going to be through R9. So R15 is completely out of the data path. It's still in the control plane, sure, but it's out of the data path completely. So R15 is able to prune itself out of the group. And pruning essentially means that, hey, I've got no more interested receivers I need to handle traffic for. I'm not involved in this group anymore. That's the SPT switchover, and it's enabled by default. If you want to disable it, for some reason, there are valid reasons, but most of the time you want to keep it default. But if for whatever reason you do want to change it, IPPIM SPT threshold is going to allow you to specify either to 0, which always switches to the source tree when it can, or infinity, which is going to never switch to the source tree. It's going to stay on the rendezvous point tree at all times. The default is 0 because it switches over to the SPT. But infinity is going to make it so that we stay on the shared tree at all times. We don't switch over. that's the SVT switchover. The other thing was packet captures. So that's the last thing we're going to cover here, and then I'm probably going to sign off because I have a test tomorrow I need to take.
Oh, well.
Yep.
Saturday?
So
test on Saturday?
Yep. Do you guys in Japan do the SAT? I don't think so.
No. Well, they have an equivalent.
Sure, but yeah, I'm taking the SAT. I'm retaking the SAT tomorrow. I'm gunning for 1600.
Good luck.
Thanks. So what we're going to do here, so I'm going to go back to my CML, and I want to packet capture a couple of things. So we're going to packet capture the membership report. Actually, no, I think we did the membership report, right?
Yes, we saw that.
Yeah, we saw the membership report in the query, so I can skip by Gmp because that's the main two messages that we care about. We can look at the PIM joins then.
Sure.
Okay, cool. So let's see, what's the most logical point here? We're gonna have to packet capture at two places because I need to packet capture the joins and the registers. So let's look here. So I'm using H2 as my source. I'm going to keep the same group. So H2, we need to go ahead and look at the PIM register. Well, we need a packet capture from R11. And then I need to packet capture from, we'll packet capture from one of the LHRs. So we'll packet capture, LHR would be 15. Okay. So what I'm going to do is I'm going to packet capture on the link between R11 and R1 because this is the FHR. It's the first hop router from the source, which is H2. And then I'm going to packet capture on the link between R15 and R9 because that's the LHR for our H6, which is one of our receivers. So hopefully that's correct. So what we're going to do, I'm going to drag this back over so I can set the max packets correctly because it defaults to a max packet count 50. And if I were to start a packet capture with a max packet count of 50, it's going to die in about 5 seconds. So we're going to set it to 1,000 and start on both ends. Okay, so what I'm going to do is, let's look here. So PIM options. Okay, so we already have PIM joins coming in. And we're going to, cool, okay. So now what we're going to go ahead and do is ping on host 2. Host 2, we're going to go ahead and ping the Multicast group again. Cool. All right, so we got what we need, I think. And we'll ping it once again for good measure. Cool. All right, so I'm going to go ahead and stop the packet captures on both ends. I'm going to go ahead and download these locally. I'm not the biggest fan of CML's inbuilt packet capture, so I'm just going to download the PCAP and we can look at it in Wireshark.
Sure.
R11, what is this link again? R11R1. And this is going to be R9, R15. Okay, so let's see, what do I want to take a look at first? I'll take a look at the register first. So we'll take a look at R11 to R1. So we'll look for PIM and we'll look for Igmp. So you can see we have these PIM hellos here. So we have the hold time, which is 105 seconds, the DR priority, and we have some other options here, but mainly the hold time and the DR priority is what we're going to be concerned about in the hellos. We have, and you can see this is multicasted to 224.0.0.13, which is going to be the PIM-v2 all routers address that we care about. So that's the hellos and the joins. We can see here, let's see what this join is for. PIM option, so the upstream neighbor is 10.1.11.1. So this is packet capturing, this is sourcing from 11. So the upstream neighbor is going to be 10.1.11.1. That's R1, which is the directly connected PIM neighbor there. Let's go ahead and look at the groups. So 1, 2, 4, I'm going to collapse lists not the group we care about. This is the group we care about. So this is the group for 124.1. This is just refreshing that star comma G that we already had. This is the old group that I was using. I pinged 136, so this is what we care about right here. So what we have here is, firstly, we've got the group address. We've got the address family, which is IPv4. We've got bidirectional PIM not set. This is a special case for PIM. It is sparse mode, but it's used for special applications. I don't have time to cover this, but again, like I mentioned in the middle here, I will point to some resources that you can use if you want to learn about SSM and bidirectional PIM. SSM and bidir PIM are not that hard to understand. Quite frankly, if you understand sparse mode PIM, it's a pretty logical evolution. I will say bidir PIM is a lot more drastic of a change than SSM. SSM is just basically, it's the same as ASM, except we're kind of we're jumping the gun. So we're learning the source externally out of band instead of having to rely on the RP to learn a source. So which means that with SSM, we don't technically need an RP because we don't have any star comma Gs. We have only S comma Gs. Bidirectional PIM is the exact opposite. We don't have any S comma Gs at all. We have only star comma Gs. And the reasoning for each is where stuff gets complicated. So this is the group address, the mask length, which is the /32 because this is just one group that we're referring to. And then we've got prunes. So this is the join prune message. So you use, it's determining this from the type. So type 3 is both join and prune. So we have joins and prunes in the same message. So in this case, this message is what we're using the prune here. So we're pruning the rendezvous point out of the rendezvous point tree. So that's the join. And let's see, we have joins here. Yep. So we can see here pretty much the same format as a prune, except one's a prune and one's a join. So a lot of the same information is encoded, which makes sense because they're pretty similar. They're just opposites of each other. So a join would be, I want to participate in this tree. A prune would be, I don't want to participate in this tree anymore. So it's a lot of the same information. So that's that. And then a PIM register. So this is what we were talking about earlier. When a source starts sending traffic, the first hop router picks it up and then sends a PIM register out. Now, what we have here is we've got these PIM options here. Fairly unremarkable. What's remarkable here is that it's actually going to send out the data. That was the source traffic. So we've got the IPv4 here, header, and then the ICMP header. So we were pinging the multicast group, so it's going to go ahead and send out the source traffic as well. IP version IPv4. So fairly unremarkable, but this is going to go ahead and tell us what the source is and what the group is. So the source was 192.168.12.2. The destination is 239.0.1361. So this is how we're deriving the S comma G entry. We're looking at the source, and then we're looking at the destination, which is going to be our multicast group address. So that's that. Now we can go ahead and open up let's take a look, the R9, R15. And here we've got a join. So first of all, this is 15.15. And for the 136.1 group, we are joining to the rendezvous point tree. So what this is essentially saying, what 15 is saying is I have an interesting receiver that's attached to me. I learned about this interested receiver via IGMP. There's an IGMP report that the receiver sent to its directly connected router, which in the context of the path ends up being the last hop router. That router then absorbs the IGMP report, because remember, IGMP just exists between the receiver and its directly connected router. It's going to go ahead and absorb that IGMP report, and it's going to base a PIM join on that. So it's saying, okay, I want to join to the IP address of 3.4.3.4. As you recall, that's the RP. So we're joining to that rendezvous point tree, and you can see as much here. We have the rendezvous point tree flag set for the 239.0.1361 group, which means we're effectively, what this translates to is we're trying to join the star comma G. That's what that join translates to. Here, this is the second join. This doesn't have this bit set, which means that we're not joining the rendezvous point tree, we're joining the shortest path tree. So we just have the sparse mode flag set, which is true because we're running sparse mode in this topology. And you can see the IP address earlier here, because we were joining the rendezvous point tree, is the rendezvous point. But this is the SPT switchover. This is the SPT switchover join message. So what happened here was that the last hop router here, which is R15, it received the multicast traffic in. So it saw, okay, well, this is coming from a source of 192.168.12.2. So what it's doing is it's sending a PIM join towards 192.168.12.2. And this is going to be absorbed by router 11 because it doesn't, our H2 isn't running PIM. So it has no reason. There's no PIM neighborship. So R11 is not going to keep forwarding this on. But what R11 will do, which is the first hop router, what R11 will do is absorb this, and it's going to learn the join. So it's going to learn that R15 wants to join directly to the SPT. And after this, it prunes itself out of the rendezvous point tree. So now we're not sending traffic over the rendezvous point tree, we're sending it over the shortest path tree. So that's really all. That's as far as packet captures go. There are more PIM messages, obviously, to consider. This is, again, just the basics, just a crash course. But I feel that with this knowledge, you can go and read a multicast book, and you're at least aware of the basic multicast mechanisms. So you can learn about more advanced concepts like SSM or BIDR or whatever the case may be.
Yeah, for sure. I think, you covered a lot of topics. For those of you who aren't aware, like I personally don't know that much about multicast yet, so I've been learning along with you guys, and I think I'll definitely want to watch this one again and take some notes and then dive into the books, learn the details.
Yep. So hopefully, I do realize it may have been a little bit, let's say, nicely improvised, but hopefully the flow was coherent and made sense.
Yeah, for sure.
Helped you guys.
Yeah, I think it was pretty easy to follow.
The last thing was really the last thing is resources.
Yes.
So
some recommendations.
There's a couple of books that I'd recommend. There's the IP Multicast. Actually, I'll just look for Cisco Press here. So what I'm going to do actually is I'm going to go into incognito mode. Probably be a better idea here because I'm logged into my Cisco account. So going to go here. If you look for IP Multicast on Cisco Press, there's should be two books here. There's Volume 1 and Volume 2. Also, Routing TCP/IP covers, the Volume 2 covers a bit of multicast, and then IP routing also covers, I believe this also covers multicast. So we've got Volume 1 and Volume 2. These are multicast books. There's also Interdomain Multicast Routing. Might find that on Amazon. Interdomain Multicast Routing. This is the book I'm looking for. So this also covers Juniper Multicast. Same concepts for the most part, just mildly more annoying commands to implement. So we have a lot of coverage here. This is going to focus more in depth on the interdomain part. So I covered intra-domain Anycast RP using MSDP. This is going to take more of a look at applying MSDP, which is the same protocol, but it has some different applications to things like interdomain multicast. So there's some extra hoops you have to take because because RPF is going to rely on the unicast topology, and if you're running interdomain multicast, then there's a good chance that you're not running the same IGP domain. That both of those domains are going to run independent IGPs. So you do have to take some extra steps to make sure you do have routing reachability in the underlying unicast topology in order for interdomain multicast routing to work. And that's where you get into a lot of the more fun features that I didn't get to cover here, like BGP to do the RPF signaling, stag IPM routes, things like that. So definitely if you want to cover multicast, these two books are going to be your godsend to you. And then inter-domain multicast routing is just going to build on top of some of that knowledge by covering the inter-domain side of things. And all 3 books I've read through to some extent, at least. I haven't finished all of them, but all 3 books I've read through to some extent, and they're good books. So I highly recommend them if you want to look more at IP multicast. There's also some good courses. So there is INE, obviously. So Brian McGahan, Rohit Pardesani, all those guys have made multicast courses. There are focuses on things like VXLAN there. So if you want to take a VXLAN course, you'll cover multicast there. CBT, I think, covers some multicast. I haven't looked at CBT in a while, but I'm sure they have some multicast content. So there's a variety of multicast sources out there. And worst case scenario, you can always just go to Cisco support here, router, or actually networking software. And let's say we want 17 here, documentation, and we're looking for configuration and view all documentation in this type. And again, well, not again, but if you're doing the CCIE exam, it is a good thing to get used to this, because if you are on the CCIE exam, this is what you have access to documentation-wise. So it's a very good idea if you're learning multicast in the context of a CCIE exam. It's a very good idea to get familiar with how to navigate the Cisco support page. So in the event that you do have to on and off reference the documentation, again, the keyword is on off. You want to utilize documentation wisely. It's not an easy out. It's there for you to utilize wisely. But if you do need to reference it for some multicast stuff, IP multicast routing here. And we've got a bunch of things here. We've got the technology overview. So this is a lot of what I covered here and a lot of what I didn't. So things like the translation between layer 3 and layer 2 multicast addresses. We can configure basic IP multicast for v4. This is where we get into SSM and Bsr, which I didn't cover here. There's also a lot here that I did cover. AutoRP, Anycast RP, Bsr, SIG-RP. This is IPv6 multicast, MSDP for inter-domain multicast, source-specific multicast. I wanted to cover this. We didn't get time. This is multicast tunneling. So this is where you start to get into the complexities of RPF, that the loop prevention mechanism we talked about. There's BFD support for PIM. There's FHRP aware PIM, which is fun. And yeah, so this is a very good source of documentation if you need to reference it. So again, the main point here is if you're willing to look, there's a multitude, there's a plethora of multicast resources out there for you to reference.
All right, sounds good, yeah. This Cisco documentation is always a great resource, I think, no matter what you're studying.
Indeed. And I mean, Juniper has some docs too. If you need to work with multicast on Juniper, they have some good. I wouldn't say it's nearly as good as Cisco's docs, mainly because multicast, in my opinion anyway, is far more annoying to implement on Juniper. But if you do need to reference it, Juniper has some good tech docs on the subject.
Cool. All right.
So that's it for me.
Awesome. Thanks.
I'm going to go ahead and stop the screen share.
Yeah, sure. I'll return to our cameras and we'll wrap this up.
Stop sharing.
All right. We're both back on screen. All right, Kelvin, thanks for your time. That was awesome. Great introduction to a lot of important topics about multicast. Yeah, so definitely, if you guys are looking into learning multicast, watch the stream again, take notes, try it out in a lab, ideally get CML and actually try it out, configuring it yourself.
Yeah, definitely.
And look into those recommendations that Kelvin gave at the end. All right, so good luck on your test tomorrow. Get a good rest. Where can everyone find you? You're on YouTube. I link your channel in the description, by the way. So subscribe to my YouTube.
I'm on LinkedIn. I have a Twitter that I only read because I have no interest in actually participating in Twitter. I just use it to catch up with the world. So you can find me on Twitter and follow me there, and people have found me there. It's just that don't expect me to actually post any more often than once in a blue moon.
Yeah, fair enough.
If you want to reach me, the best place to do so is either LinkedIn or Discord. I'm on your Discord. I'm an admin in Chuck's Discord and David's Discord and in Keith's Discord. So I I'm not a staff on Cisco study group, but I float around there. And so you'll find me in any of those Discords.
Any of the big networking Discords, he'll be on there. So feel free to join, ask questions.
I'm not hard to find.
Yeah, yeah. All right. Oh, we have one question. Is multicast important for CCNA? No, not really.
What I've covered.
Yeah, this is beyond that.
Yeah, understanding what multicast is, I would contend is important for the CCNA. So knowing that multicast is one to many, and understanding the differences between that, unicast, and broadcast, you could say it's important for the CCNA. But things like Igmp and PIM and how you actually operate multicast, that's getting into the CCNP because it relies on, as you've seen here, I've mentioned unicast a lot. It relies on a very good understanding of unicast. So, and that's what you're gonna get in the CCNA. So that's why CCNA doesn't really cover multicast with all that much detail.
Yeah, right. Okay, thanks. I think we'll wrap it up here. Thanks everyone for watching. Thanks again to Kelvin for his time and for showing us about multicast. See you guys next time.